Imagine a force so immense that it pulls entire galaxies toward it, yet remains unseen, lurking in the depths of the cosmos. This is just one of the mind-bending phenomena that shape our universe. From galactic collisions that illustrate the chaotic dance of celestial bodies, to the brilliant explosions of supernovae that forge the very elements of life, the cosmos is alive with events that challenge our understanding. The Great Attractor is a vast, mysterious region in space that exerts an incredible gravitational pull on nearby galaxies. Located about 200 million light-years away from Earth, this colossal gravitational anomaly is believed to be at the heart of a massive concentration of matter. Although we cannot see it directly, scientists suspect it consists of a cluster of galaxies and dark matter, making it a pivotal influence in our cosmic neighborhood. As galaxies move through space, the Great Attractor affects their trajectories, causing them to move toward it. This motion is not merely a gentle drift, but a robust gravitational dance. For instance, our own Milky Way galaxy and its neighboring Andromeda, along with many others, are being drawn towards this massive entity. The weight of the Great Attractor is akin to a whirlpool in a vast cosmic ocean, pulling everything nearby into its depths. Moreover, the Great Attractor is part of an even larger structure known as the Laniakea supercluster, which encompasses thousands of galaxies over a vast expanse. The Laniakea supercluster itself is part of the universe's grand tapestry, stitched together through the forces of gravity. This interconnectedness shows us how expansive and dynamic the cosmos truly is, with regions influencing each other's movement far beyond what our eyes can see. Research into the Great Attractor is ongoing, with many questions still unanswered about its exact composition and overall structure. However, it serves as a reminder of the complexities of our universe, illustrating how even the seemingly empty space around us is filled with gravitational forces that shape the cosmos on a grand scale. As we look deeper into space, we uncover more mysteries, revealing the intricate web of interactions that govern the dance of galaxies in the cosmos. The Great Attractor is located approximately 100 million light-years away from Earth, in the direction of the Centaurus constellation. This immense distance means that, while we experience its gravitational influence, the actual journey to this cosmic enigma would take an incredibly long time, far exceeding the lifespan of any human endeavor. The Great Attractor is a focal point of mass in the universe, drawing galaxies, including our own Milky Way, toward it with its extraordinary gravitational pull. This gravitational effect has fascinating implications for our place in the cosmos. Instead of existing in isolation, our galaxy is continuously moving, participating in a cosmic ballet influenced by various gravitational entities in the universe. This movement is part of a larger flow toward not just the Great Attractor, but also a region called the Laniakea supercluster, which encompasses around 100,000 galaxies. Together, these cosmic forces shape our galactic neighborhood and our place within it. Moreover, the Great Attractor serves as a reminder of how interconnected the universe is. Despite the vast distances separating us, everything we see in the night sky is part of a larger web of forces and energy. The forces at play over such enormous distances can affect galaxy formation and evolution, providing a compelling perspective on how the universe operates on grand scales. As scientists continue to study the Great Attractor, they unlock deeper understandings of cosmic behavior and structure. The mysteries surrounding this massive gravitational anomaly not only deepen our knowledge of physics, but also evoke a sense of wonder about the intricate dance of galaxies, highlighting just how dynamic and interconnected our universe truly is. The Great Attractor is a fascinating cosmic feature, a region of space that exerts a significant gravitational pull on our Milky Way galaxy, among others. Located in the direction of the Centaurus constellation, this immense gravitational force originates from a concentration of mass, including galaxies and clusters that lie hidden behind dense fields of stars. As our galaxy moves closer to this mysterious region, scientists believe it will have lasting impacts on its structure and future. One of the most notable changes scientists anticipate is related to the Milky Way's own movement. As we are drawn toward the Great Attractor, our galaxy is on a journey through the vast expanse of space, moving at an impressive speed of around 270,000 miles per hour towards this gravitational beacon. This motion is not just a simple shift, it will affect the spatial relationships between the Milky Way and its neighboring galaxies, leading to a dynamic reconfiguration of our cosmic net. As we approach the Great Attractor over the coming millions of years, it is expected that our galaxy will experience increased interactions with nearby galaxies. Such interactions can prompt a variety of phenomena, including gravitational encounters, mergers, or even distortion of galactic shapes. These cosmic dances can give birth to new stars, or even radically alter the orbits and positions of existing stars within our galaxy. Eventually, the gravitational forces at play will reshape not only our galaxy, but also the surrounding galactic structure. Whole clusters could align in unexpected ways, leading to new patterns of cosmic organization. In this ever-evolving cosmic ballet, understanding the Great Attractor helps us appreciate not only our own Milky Way's fate, but also the intricate tapestry of the universe we inhabit. The Great Attractor is a mysterious region of space that draws galaxies towards it with an immense gravitational pull. Located around 200 million light-years away, this gravitational anomaly is estimated to contain a vast collection of galaxies, gas, and dark matter. However, studying it directly poses significant challenges for astronomers. One major difficulty comes from our position within the Milky Way galaxy. Earth is situated in a part of the Milky Way that is filled with stars, gas, and cosmic dust, which act like a dense veil obscuring our view of the Great Attractor. This cosmic clutter blocks the light from the galaxies behind it, making it hard to observe them directly. Imagine trying to see something distant through fog. The more dense the fog, the more challenging it becomes to spot objects on the other side. Additionally, the Great Attractor is not a single object that can be pinpointed easily. It is part of a larger cosmic structure called the Laniakea supercluster, which contains thousands of galaxies. As a result, the Great Attractor is not just an isolated phenomenon, but rather a complex mix of various galactic movements and distributions. This complexity adds another layer of difficulty in isolating what exactly is happening in that region of space. Lastly, much of the mass associated with the Great Attractor is made up of dark matter, which does not emit light or energy that we can detect using conventional telescopes. This mysterious and elusive substance makes it even more challenging for astronomers to gather data on the Great Attractor. They rely on indirect methods, such as observing the movement of nearby galaxies, to piece together the influence of this enigmatic region. So, while the Great Attractor holds many secrets within its depths, our limited vantage point and the nature of cosmic objects make it an enduring puzzle for scientists. The Great Attractor is an unseen gravitational force, a region in space that appears to draw galaxies towards it, notably affecting the motion of our own Milky Way. It lies at the center of a massive structure called the Laniakea supercluster. Its immense gravitational field causes galaxies to accelerate toward it, hinting at a significant amount of unseen mass. This phenomenon aligns closely with the concept of dark matter, the mysterious substance thought to make up a considerable portion of the universe's mass. As we study the gravitational effects of the Great Attractor, we glean vital clues about the nature and distribution of dark matter. The motion of galaxies towards this massive hub suggests that dark matter surrounds us in a cosmic web, influencing how matter clumps and forms structures in the universe. Understanding the dynamics at the Great Attractor helps provoke questions about the prevalence and characteristics of dark matter across larger scales. This relationship may redefine our models of how galaxies and structures are formed and interact. Furthermore, as researchers investigate the data collected from the movement of galaxies in the vicinity of the Great Attractor, we are uncovering more about the role dark matter plays in shaping the universe. Current models propose that dark matter does not only envelop galaxies, but also interacts with regular matter in complex ways. This understanding could potentially lead to breakthroughs in how we perceive dark matter itself, propelling new theories and experiments in particle physics to uncover its true nature. The eventual movement of our galaxy towards the Great Attractor serves as a pivotal focus for scientists seeking to decode the mysteries of dark matter. Each revelation keeps us on the edge of our seats, inspiring curiosity about the unseen forces of the universe and encouraging a deeper exploration of what truly makes up the cosmos around us. The journey to grasp dark matter's role and impact is ongoing, and through the Great Attractor, we might be getting closer to the answers we've been seeking. The Milky Way galaxy, our home in the cosmos, is on a collision course with the Andromeda Galaxy, its nearest large neighbor. This cosmic event is expected to unfold over a staggering timeline, with estimates suggesting that the collision will begin in approximately 4 billion years. This may seem like a distant future, yet in cosmic terms, this is just around the corner. As these two galaxies approach each other, they will not collide in a sudden cataclysmic explosion. Instead, the process will take millions of years, resulting in a gradual merging of the galaxies. Over the course of these billions of years, the gravitational forces between them will cause changes in their shapes and structures. The stars within each galaxy are so far apart that they will largely pass by one another unscathed. However, the gravitational interactions will stir gas and dust, igniting new star formation in regions where these materials collide. When the Milky Way and Andromeda do merge, they will create a new galaxy, often referred to as Milkomeda, a nickname that captures the blending of both names. This new entity will be a spectacular sight, albeit vastly different from what we see now. Our solar system, which is about 25,000 light-years from the center of the Milky Way, may find itself in a different position within this merged galaxy, possibly even closer to the galactic center. While this timeline is incredibly long from our perspective, it serves as a reminder of the dynamic and ever-changing nature of the universe. The fate of galaxies is intertwined, reminding us that in the grand tapestry of the cosmos, change is not only inevitable, but also a source of beauty and wonder. So as we gaze up at the night sky, we can appreciate it for what it is now while pondering the extraordinary future that lies ahead. The anticipated collision between the Milky Way and Andromeda galaxies, set to occur in about 4 billion years, is a profound event for both galaxies. However, it's important to clarify that the impact of this collision on individual solar systems, like our own, will not be as disastrous as one might imagine. Despite the dramatic imagery often associated with galactic collisions, the vast distances between stars mean that direct star-to-star collisions are exceedingly rare. As the two galaxies approach each other, their gravitational interactions will significantly reshape both of their structures. Stars and solar systems will experience shifts in their orbits as gravitational forces tug at them. For instance, our solar system, located in one of the Milky Way's spiral arms, may find itself in a different region of a newly formed galaxy after the collision, perhaps even part of a new galactic structure entirely, but rather create new dynamics that influence how stars and solar systems evolve. Interestingly, this merger of galaxies will also stimulate star formation. The gravitational disturbance will compress gas and dust in certain areas, leading to an increase in new stars being born. This burst of star formation could lead to visible changes across the galaxies. It is a reminder of the cosmic cycle of creation that is driven by interactions at such grand scales. Ultimately, while the Milky Way and Andromeda are on a collision course, the long-term effects on our solar system are complex, but likely to be more transformative than catastrophic. This cosmic dance illustrates the ever-changing nature of the universe, where collisions can lead to both chaos and the birth of new stars, creating an awe-inspiring legacy for the galaxies involved. Studying the dynamics of galaxy collisions provides a fascinating glimpse into the evolutionary history of galaxies. When two galaxies collide, they do not simply pass through each other. Instead, their gravitational forces interact, dramatically altering their shapes, star formation activities, and even their eventual fate. This interaction can lead to the merging of galaxies, creating larger and more complex structures over time, which is crucial for understanding how galaxies evolve. One of the most direct insights from these collisions is the impact on star formation. When galaxies collide, they trigger waves of new star formation. The gas and dust in each galaxy get squeezed together, igniting the birth of countless new stars. This process helps astronomers piece together the timeline of star formation across different types of galaxies and at various points in the universe's history, helping us understand how galaxies grow and evolve over billions of years. Additionally, studying these collisions can reveal the presence and influence of dark matter. Galaxies are surrounded by halos of dark matter, a mysterious substance that does not emit light and cannot be seen directly. The gravitational effects of this dark matter influence the dynamics of galaxy interactions and can be studied through the motions of stars and gas. This information helps scientists unravel the role dark matter plays in the formation and evolution of galaxies, enhancing our comprehension of the universe's structure. Finally, galaxy collisions also act as natural laboratories for testing theories of galaxy formation and evolution. By observing various collision scenarios, astronomers can develop simulations to predict how different types of galaxies behave during interactions. These insights not only shed light on our own Milky Way's history, including its past encounters and future collisions, but they also help us understand the larger cosmological environment in which galaxies exist and evolve over time. This ongoing research continues to open new avenues of understanding in the fascinating story of the cosmos. To grasp how we might simulate the effects of a galactic collision on Earth, we must first appreciate the enormity of the cosmos and the scale of galactic structures. Our galaxy, the Milky Way, is immense, stretching about 100,000 light-years across, teeming with billions of stars, planets, and interstellar matter. When two galaxies approach each other, the forces of gravity initiate a complex dance that can result in various outcomes, from merging to merely grazing past one another. Scientists primarily utilize computer simulations to recreate the conditions and interactions that would occur during such colossal events. These simulations incorporate the laws of physics, specifically gravity, as well as the dynamics of gas and stars, composition and velocity of the galaxies involved, allowing them to visualize changes over millions or even billions of years. What unfolds in these digital realms can be astonishing, revealing how galaxies stretch, distort, and eventually collide, creating new star-forming regions and altering structures dramatically. Now, engaging with the perspective of Earth, we also consider how such grand celestial events could impact our home planet. Although our location within the Milky Way remains largely stable, those simulations can illuminate potential catastrophic events like increased cosmic radiation or significant shifts in gravitational fields. These disturbances could affect everything from our atmosphere to the orbits of celestial objects within our solar system, although the likelihood of a direct collision affecting Earth is extremely low given the vast emptiness of space. Finally, as researchers analyze these simulations, they often share their findings with the public through visualizations that are both profound and eye-opening. The process illustrates not only the beauty of cosmological events, but also showcases our human curiosity in understanding the universe. These simulations offer a glimpse into a future shaped by galactic forces, nurturing our wonder for what lies beyond our world while grounding us in the reality of our cosmic neighborhood. Galactic collisions often conjure images of chaos and destruction, reminiscent of epic science fiction battles. However, the reality of these cosmic events is quite different. While large galaxies clash with each other, the vast distances between stars mean that direct star-on-star collisions are exceedingly rare. In fact, when two galaxies collide, most of the stars simply pass by one another, much like cars moving across a busy intersection without actually crashing into each other. Instead of violent collisions, galactic mergers result in a complex dance of gravitational interactions. The gravitational forces at play can lead to spectacular phenomena, such as the reshaping of galaxies, the triggering of new star formation, and the creation of supermassive black holes at the centers of the newly formed galaxies. During these collisions, gas and dust clouds within the galaxies compress and heat up, leading to the birth of countless new stars, sometimes giving rise to vibrant starburst galaxies. Another misconception is that these collisions happen quickly. In fact, galactic mergers unfold over millions to billions of years, making them some of the slowest-paced yet most profound processes in the universe. As galaxies approach each other, they might experience several close encounters. This gradual blending creates intricate cosmic tapestries that reveal the history of our universe. Ultimately, while the imagery of galaxies colliding might conjure thoughts of violence and destruction, these encounters are more about transformation and rebirth. As the to and fro of stars and gas leads to new forms and structures, the universe takes on a sense of continuity, a reminder that even in potential chaos, there is a graceful order in the cosmos. A supernova is an enormous explosion that occurs at the end of a star's life cycle. This spectacular event can outshine entire galaxies for a brief period. The light and energy produced during a supernova can be observed across vast distances in space, making these celestial phenomena some of the most studied events in astrophysics. Supernova can happen in two main ways, linked to different types of stars. The first type occurs when a massive star, one that has at least 8 times the mass of our Sun, exhausts its nuclear fuel. Once the nuclear reactions cease, the outward pressure that keeps the star's core from collapsing disappears. The core, now devoid of energy, succumbs to gravity, collapsing into a dense object. This catastrophic collapse leads to a rebound effect that results in the outer layers being expelled into space at incredible speeds. The second type of supernova occurs in binary star systems, where one star siphons matter from its companion. When a white dwarf star in such a system accumulates enough material, it reaches a critical mass, triggering a runaway nuclear fusion reaction. This causes the white dwarf to explode in a brilliant flash. This type is known as a Type Ia supernova and serves as a vital tool for measuring cosmic distances due to its consistent luminosity. Supernovae not only mark the dramatic deaths of stars, but also play a crucial role in the cosmos. This redistribution of materials is essential for the formation of new stars and planets, linking the life cycles of stars to the broader evolution of the universe. So, in every supernova, we see not just destruction, but also the seeds of future worlds taking shape in the vastness of space. Astronomers are particularly excited about the potential visibility of supernovae from distant events, because these spectacular explosions provide a unique glimpse into the universe's past. Each supernova is like a cosmic beacon, releasing an extraordinary amount of energy and light, often outshining an entire galaxy for a brief period. When these celestial phenomena occur in galaxies millions or even billions of light-years away, they not only fascinate astronomers, but also serve as valuable markers for studying the expansion of the universe. One of the key reasons supernovae are so significant is that they can help us understand the life cycles of stars and the formation of elements. During a supernova explosion, massive stars eject heavy elements into the surrounding space, enriching the interstellar medium with materials that contribute to the formation of new stars, planets, and even life. By observing supernovae from different distances, astronomers can analyze the chemical composition of these elements, enhancing our understanding of cosmic evolution. Additionally, distant supernovae act as crucial tools for measuring the expansion rate of the universe. In the late 20th century, 2 research teams used observations of supernovae to discover that the expansion of the universe is accelerating, leading to the groundbreaking concept of dark energy. This has transformed our understanding of cosmology, as it suggests a mysterious force driving this acceleration. By continually monitoring new supernovae, astronomers can refine their measurements of this cosmic expansion. Finally, each supernova carries with it information about its host galaxy. The characteristics of the supernova, including its brightness and light curve, can reveal details about the galaxy's composition, age, and size. The potential to capture and study more distant supernovae opens new doors for exploration, allowing us to piece together the puzzle of our universe's history while igniting a sense of wonder about the vast cosmos surrounding us. If a supernova were to occur close to Earth, within just a few dozen light-years, it would unleash an astonishing amount of light and radiation, far exceeding what our Sun emits in a single day. This stellar explosion happens when a massive star reaches the end of its life cycle, collapsing under its own gravity and igniting a dramatic explosion. The light from this event can be so intense that it might be visible in daylight, turning the night sky into a brilliant spectacle. The radiation produced in such an explosion includes not only visible light, but also harmful ultraviolet and X-ray emissions. This high-energy radiation could pose significant risks to our planet's atmosphere. While Earth's atmosphere provides a protective shield, an explosion sufficiently close could deplete the ozone layer, which serves as a barrier against harmful ultraviolet radiation from the Sun. Interestingly, even if a supernova is well within the dangerous range, Earth's atmosphere and magnetic field would mitigate some of the effects. The atmosphere absorbs many forms of radiation, and the magnetic field helps deflect charged particles. However, scientists believe that a supernova occurring too close could still interrupt the delicate balance of life on our planet, causing a cascade of ecological consequences. In discussing supernovae, we must also consider their role in the broader universe. These explosions distribute heavy elements throughout space, enriching the interstellar medium and providing the building blocks for new stars and planets. So, while a nearby supernova could pose threats to life on Earth, It would also contribute to the cosmic cycle of creation and destruction, shaping the universe around us in profound ways. The life cycle of a star is a fascinating journey that spans millions to billions of years, ultimately leading to one of the universe's most spectacular events, a supernova. This process begins with a vast cloud of gas and dust in space, primarily composed of hydrogen. Under the influence of gravity, this cloud slowly collapses, forming a dense core that heats up over time. Once the core reaches the necessary temperature and pressure, nuclear fusion ignites, and the star becomes a shining beacon of light, embarking on a stable phase known as the main sequence. During its main sequence phase, which can last for billions of years, a star fuses hydrogen into helium in its core. Our Sun is currently in this stage. As the hydrogen fuel diminishes, the balance between gravitational forces pulling inward and the energy from nuclear reactions pushing outward begins to shift. For massive stars, those significantly larger than our Sun, this leads to the next chapter of their lives, as the core contracts and heats up, allowing the fusion of heavier elements such as helium into carbon, and eventually progressing to even heavier elements like iron. Once iron is formed in the core, things take a crucial turn. Iron fusion does not produce energy. Instead, it consumes energy. This signals the collapse of the core. When the core becomes too dense and heavy to support itself against gravity, it collapses in a matter of seconds, creating an extremely high-pressure environment. This sudden collapse triggers an enormous explosion, the supernova, where the outer layers of the star are ejected into space at incredible speeds, while the core can be left behind as either a neutron star or a black hole, depending on its mass. This explosive event is not just a spectacle, it has far-reaching consequences for the universe. The materials expelled during a supernova enrich the surrounding space with elements like carbon, oxygen, and iron, which are essential for the formation of new stars and planets. Thus, the life cycle of a star is not just a solitary journey, it is a vital component of the cosmic tapestry, enabling the creation of new worlds and the continuation of the cycle of life in the universe. Supernovae, the cataclysmic explosions of dying stars, have played a fascinating role in shaping not only the cosmos, but also our own planet's atmosphere. When a supernova occurs in our galaxy, it releases a staggering amount of energy, equivalent to the luminosity of an entire galaxy for a brief period. These explosions can send shockwaves through space, and when a supernova occurs relatively close to Earth, its effects can ripple through our atmosphere and even impact the biosphere. Historical evidence suggests that supernovae may have contributed to changes in Earth's atmosphere, particularly during pivotal moments in our planet's history. For instance, scientists believe that a supernova explosion occurred around 8,000 light-years away from us, in the constellation Cassiopeia, roughly 2 million years ago. The radiation and cosmic rays from this event likely influenced climate patterns, possibly contributing to the fluctuations in temperature and conditions during the Pleistocene epoch, which saw the rise and fall of ice ages. Furthermore, cosmic rays generated by supernova can stimulate the formation of clouds and influence weather patterns. When these high-energy particles collide with atmospheric molecules, they can lead to ionization, which acts as a catalyst for the creation of cloud condensation nuclei. This process is essential for cloud formation, and some studies indicate that supernovae might have played a role in climate variations by altering cloud cover and precipitation patterns. In addition to their climatic influences, supernovae distribute vital elements such as carbon, oxygen, and iron across the universe. These elements are crucial for life and have been recycled through various cosmic processes to become part of the molecular building blocks we find on Earth today. Thus, while supernovae are catastrophic events, they also serve as essential mechanisms for creating and dispersing the elements that sustain life, weaving a complex narrative in the history of our atmosphere and the development of life on our planet. Alpha Centauri, our closest star system, located just over 4 light-years away, is a fascinating region of study for astronomers and astrophysicists. This binary star system, composed of Alpha Centauri A and Alpha Centauri B, has intrigued scientists not only because of its proximity, but also due to the potential for variability in its stellar characteristics. If these stars undergo significant changes, it could reshape our understanding of exoplanets, which are planets orbiting stars outside our solar system. Changes in the conditions around Alpha Centauri would profoundly influence any exoplanets that might orbit these stars. For instance, if one of the stars were to enter a phase of increased brightness or a change in stellar activity, the habitability zones of the surrounding planets could shift dramatically. This means that planets previously considered too hot or cold for life might find themselves in a more favorable position, or vice versa. These alterations could lead to new questions regarding the atmospheric conditions and potential habitability of these exoplanets, making scientists reconsider their previous assessments. Moreover, significant changes in Alpha Centauri could also provide insights into the broader dynamics of exoplanet formation and evolution in binary star systems. Churning gravitational forces and varying radiation levels can dramatically affect the orbits and climates of planets nestled among these stars. The study of these effects would enhance our knowledge, revealing how common or rare similar processes could be in the universe. This can lead to broader implications for understanding which systems may support life and how we detect these opportunities. Thus, the potential variability in Alpha Centauri enriches both our curiosity and scientific inquiry. Each revelation about this nearby star system serves as a stepping stone, guiding researchers towards deeper truths about exoplanets in countless other solar systems. It's a reminder that the universe is full of dynamic processes, constantly reshaping the landscape of what we think we know about worlds beyond our own. Alpha Centauri, located just over 4 light-years from our planet, is a fascinating binary star system comprised of 2 stars, Alpha Centauri A and Alpha Centauri B. Both of these stars have similarities to our own Sun, which opens intriguing possibilities for future space exploration. The proximity of Alpha Centauri means that it is one of the most likely candidates for human exploration beyond our solar system, particularly as we search for potentially habitable planets in other stellar systems. The presence of 2 stars creates a unique environment that could influence any surrounding planets. For instance, planets orbiting in the habitable zones of these stars might experience fluctuations in light and heat due to their binary nature. This could affect climate conditions, making the potential for life even more complex. Understanding how these planets behave around 2 suns allows scientists to develop more precise models. Additionally, the relatively short distance to Alpha Centauri raises the question of propulsion technologies for interstellar travel. Current rocket technology would require an impractical amount of time to reach this star system. However, concepts like light sails or nuclear propulsion are being explored, which could significantly reduce travel time. If scientists succeed in developing these advanced technologies, it could redefine our capabilities in exploring not just Alpha Centauri, but other star systems as well. Finally, the cultural and philosophical implications of exploring a binary star system are profound. The idea that we might someday set foot on a planet orbiting another sun fuels our imagination and expands our understanding of life's possibilities in the universe. Studying Alpha Centauri also offers an opportunity to reflect on our place within the cosmos, reminding us of the vastness of space and the interconnectedness of all stars and planets. In many ways, exploring Alpha Centauri can serve as a springboard not just for scientific advancement, but for inspiring future generations to look beyond and consider what lies among the stars. Alpha Centauri is often regarded as one of the most promising candidates in the quest to discover alien life due to its remarkable proximity to our own solar system. Located just over 4 light-years away, this stellar system is not only the closest, but it is also home to 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Among these, Proxima Centauri has sparked significant interest because it hosts at least one confirmed exoplanet that resides within the so-called habitable zone, a region where conditions may be just right for liquid water to exist. The habitable zone is a crucial concept in astrobiology, as liquid water is seen as one of the fundamental ingredients for life as we know it. The planet orbiting Proxima Centauri, named Proxima Centauri b, is slightly larger than Earth and is located within this zone. Although not much is known about its atmosphere or surface conditions, its position raises tantalizing possibilities about its potential to support life form. This appeal becomes even more pronounced when we consider that other planets, often called super-Earths, have been found around various stars, some of which could also be inhabitable zones. Moreover, The interest in Alpha Centauri is bolstered by advancements in technology and astronomy that enable us to study these distant worlds in greater detail. Current and future telescopes, such as the James Webb Space Telescope, are engineered to scrutinize the atmospheres of exoplanets for signs of biological activity, like the presence of oxygen or methane, which on Earth are often indicators of life. The ability to analyze light that passes through a planet's atmosphere as it transits in front of its star offers scientists a unique opportunity to search for potential biosignatures. Lastly, Alpha Centauri captures the imagination not just for its scientific potential, but also for its cultural significance. It has long been a symbol of hopes for interstellar exploration, highlighted by ambitious projects such as Breakthrough Starshot, which aspires to send tiny, light-propelled spacecraft to the Alpha Centauri system within decades. As we look toward the stars with a sense of wonder, this closest neighbor stands as a beacon of possibility, enticing us with the prospect of discovering whether we are alone in the universe or if life exists among the celestial wonders of Alpha Centauri. To observe Alpha Centauri's changes closely, several technological advancements could prove invaluable. One of the most promising tools is the development of advanced telescopes, particularly space-based observatories. These instruments, like the James Webb Space Telescope, are designed to capture not only visible light but also infrared and other wavelengths. This capability allows astronomers to study the atmospheres of exoplanets and detect faint signals that might indicate changes in the star system, including shifts in its brightness or the movement of planets around it. Another key advancement lies in the use of high-precision instruments like interferometers. By combining the light gathered from multiple telescopes, these devices can achieve incredibly high resolution, enabling astronomers to discern finer details in the Alpha Centauri system. This type of technology can help clarify the structure surrounding the stars, revealing phenomena such as stellar flares or variations in light caused by orbiting celestial bodies. Alongside these advancements, the rise of artificial intelligence in data analysis is revolutionizing how we process astronomical information. AI can sift through enormous amounts of data much faster than humans, identifying patterns or anomalies that may indicate significant changes. For instance, machine learning algorithms can analyze light curves, the graphs depicting brightness over time, to spot subtle fluctuations that suggest the presence of new planets or changes in star behavior. Lastly, the concept of interstellar probes, while still in its infancy, could provide an unprecedented opportunity for close observation. Projects like Breakthrough Starshot aim to send tiny spacecraft to Alpha Centauri within a couple of decades. If successful, these probes could relay data back to Earth, offering direct insights into the environment of this closest star system, including its planets and any changes occurring there. Together, these advancements not only expand our observational capabilities, but also ignite our curiosity about the cosmos just beyond our reach. As we look to the stars, significant changes in technology and science hold the promise of making interstellar travel a reality for future generations. One of the most critical aspects influencing this quest is the rapid advancement in propulsion systems. Innovations in fields like ion propulsion and nuclear thermal engines could deliver the necessary thrust to reach speeds that were once considered impossible. Imagine a spacecraft that could travel at a significant fraction of the speed of light, drastically reducing travel time to nearby star systems. This enhancement in speed might enable humanity to not only reach these distant worlds, but also to explore them more thoroughly. In addition, our understanding of life support systems will evolve. As mankind prepares for long journeys into the cosmos, developing sustainable habitats and technologies becomes essential. Future explorers may live aboard self-contained ecosystems capable of recycling air, water, and waste. These advancements in life support could allow generations to thrive on spacecraft for extended periods. Furthermore, the integration of artificial intelligence and robotics into these life support systems may significantly enhance the safety and efficiency of these long voyages, allowing travelers to focus on exploration and scientific discovery. Moreover, the cultural and societal shifts resulting from current space exploration initiatives may pave the way for a renewed interest in interstellar missions. Today's younger generations, inspired by achievements like Mars rovers and the study of exoplanets, might carry an insatiable curiosity that fuels the desire for exploration beyond our solar system. Education and public interest in space science can lead to greater investment and support for ambitious projects aimed at identifying habitable worlds, which in turn increases the feasibility of manned interstellar missions. Finally, the quest for interstellar travel is not just a matter of technology, it's also an endeavor grounded in global cooperation. As nations and private organizations increasingly collaborate on space initiatives, they can share resources, knowledge, and expertise. This collective approach not only accelerates technological advancements, but also unites humanity in a common goal, reaching for the stars. Future generations may find themselves working together seamlessly, driven by a shared vision of exploration and discovery, making interstellar travel an attainable objective of our time. The cosmic microwave background radiation, often referred to as CMB, is a faint glow that fills the universe and serves as a critical piece of evidence for our understanding of cosmology. This radiation is a remnant from the early universe, specifically from a time just after the Big Bang, when the cosmos was hot, dense, and filled with energetic particles. As the universe expanded and cooled, it eventually allowed these particles to combine into neutral atoms, releasing energy in the form of light. This light has been traveling through space for nearly 14 billion years, reaching us as the CMB we detect today. The significance of the cosmic microwave background lies in what it tells us about the early universe. Its discovery in the mid-20th century provided strong evidence for the Big Bang theory, which explains how our universe began and evolved. The CMB is almost uniform in all directions, but it contains small fluctuations in temperature. These tiny variations correspond to the density of matter in the early universe, laying the groundwork for the cosmic structures we see today, such as galaxies and clusters of galaxies. Furthermore, the CMB allows scientists to probe the universe's fundamental properties. By analyzing its temperature and polarization patterns, researchers can infer key information about the universe's age, composition, and behavior. For instance, data from the CMB has revealed that a significant portion of the universe is made up of dark energy and dark matter, substances that remain mysterious despite their prevalence. The CMB is like a snapshot of the universe's infancy, offering us a glimpse into its origins and evolution. Its study has revolutionized our understanding of cosmology and continues to spark curiosity, providing invaluable insights into the nature of our universe and the forces that shape it. The cosmic microwave background, often called the CMB, serves as a remarkably detailed snapshot of the universe when it was just around 380,000 years old. At this time, the universe had cooled enough for protons and electrons to combine and form hydrogen atoms, allowing photons of light to travel freely for the first time. Before this moment, the universe was a hot, dense fog, but once the CMB was released, it escaped into space, carrying vital information about the conditions that existed then. Scientists study the CMB to glean insights into the early universe's temperature fluctuations. These fluctuations are akin to ripples on a pond, representing variations in density. Where these ripples were more pronounced, matter would eventually clump together to form galaxies, stars, and all the structures we observe today. By analyzing the patterns and intensity of these fluctuations, cosmologists can draw conclusions about the composition of the universe, including the proportions of normal matter, and dark energy. Moreover, the CMB provides evidence for the Big Bang theory, which posits that the universe began from an extremely hot and dense state around 13.8 billion years ago. The uniformity of the CMB radiation across the sky supports this idea, as it suggests that the universe was once in a much more homogeneous state before it began to expand and cool. Any variations observed in the CMB offer critical clues about the forces acting in the early universe, including the inflationary period, a rapid expansion that occurred just after the Big Bang. Finally, studying the CMB helps scientists refine their models of cosmic evolution. By comparing the CMB data to theoretical predictions, researchers can better understand not only how galaxies and larger structures formed over billions of years, but also how the universe will continue to evolve. Each discovery leads to new questions, allowing us to peel back the layers of cosmic history and deepening our appreciation for the vast, intricate tapestry that is our universe. When researchers set out to measure the cosmic microwave background, or CMB, they encounter several intricate challenges. First and foremost, the CMB is an extremely faint signal that comes from the very early universe, about 380,000 years after the Big Bang. Despite its soft glow, the CMB is drowned out by a cacophony of other electromagnetic radiation from our own galaxy and beyond. This background noise from stars, cosmic rays, and other sources of radiation must be meticulously filtered out to isolate the CMB signal they are after. Another significant challenge is the precision required in measurements. The CMB is not uniform. It contains slight temperature fluctuations that hold vital information about the universe's structure and history. To capture these minuscule variations accurately, researchers utilize highly sensitive instruments aboard powerful telescopes, like the Planck satellite. Even the tiniest error in measurement, due to equipment limitations or environmental factors like atmospheric interference, can lead to significant inaccuracies in interpreting the CMB's data. Data interpretation itself presents its own layer of complexity. Once the CMB is measured, the raw data must be analyzed through intricate mathematical models that relate these tiny fluctuations to fundamental cosmological parameters, such as the universe's age, composition, and rate of expansion. This involves sophisticated statistical methods that can be both time-consuming and conceptually challenging. Lastly, researchers must constantly update their techniques and instruments to keep up with technological advancements. As our understanding of the universe evolves and new questions emerge, so too must the methods used to explore it. Staying at the forefront of technological development helps ensure that they can continue to refine their measurements, unravel the secrets of our universe, and bring clarity to one of the most profound mysteries of modern cosmology. The cosmic microwave background, or CMB, is often referred to as the afterglow of the Big Bang, a remnant radiation that fills the universe. This ancient light provides us with a glimpse into the early universe, shining a light on events that occurred just after its inception. As we continue to explore the cosmos, our understanding of the CMB could shift dramatically, especially in the context of some impending cosmic events. For instance, as new observational technologies emerge and we uncover more about black holes or the influence of dark energy, our interpretations of the CMB data might evolve. We could discover new patterns or anomalies within its structure that correlate with these cosmic phenomena. An upcoming event, like the merger of massive galaxies or a significant cosmic explosion, may leave a mark on the CMB, allowing scientists to discern the universe's behavior in ways they had not previously imagined. Additionally, future observations of gravitational waves may also impact our understanding of the CMB. Detecting these ripples in spacetime provides a direct line into the dynamics of the universe's formation and evolution. If such waves interact with the CMB, they could reveal new insights into the inflationary period of the universe, a brief moment that set the stage for the cosmic landscape we see today. Ultimately, as we stand on the brink of new discoveries, our appreciation of the CMB could deepen, illuminating not just the early universe, but also the ongoing tapestry of cosmic events. The secrets held in the CMB are vast and continually unfolding, promising to enhance our knowledge of both the past and the future of our universe. As scientists continue to unravel the mysteries of the cosmos, future discoveries related to the cosmic microwave background, or CMB, hold immense potential for understanding the fate of the universe. The CMB is a remnant of the Big Bang, essentially a faint glow of radiation that fills the universe and dates back to a mere few 100,000 years after that monumental explosion. It serves as a snapshot of the early universe, and by analyzing its properties, researchers can glean valuable insights about the composition and structure of our universe. One of the most significant aspects of the CMB is how it helps us determine the rate of expansion of the universe. This expansion is not just happening, it's accelerating, and the mysterious force behind this acceleration is known as dark energy. By closely studying variations in the CMB, scientists can measure how this dark energy affects the fabric of space and time, informing theories about whether the universe will continue to expand forever, slow down, or even reverse course in a dramatic cosmic contraction. Moreover, the CMB holds clues about the density of different components of the universe, including normal matter, and dark energy. Each of these elements plays a role in shaping the universe's destiny. For instance, understanding the ratio of these components can illuminate scenarios ranging from a stable, endless expansion to a scenario where gravity eventually prevails, leading to a catastrophic collapse of the universe. The CMB acts as a cosmic map, guiding us through the vast labyrinth of space-time. Future discoveries in this field could answer fundamental questions about where we come from and where we are heading, ultimately uncovering the fate of our entire universe. Every measurement taken and every theory tested regarding the CMB brings us one step closer to unveiling the profound truths of existence itself. Black holes are fascinating cosmic entities born from the collapse of massive stars. When a star exhausts its nuclear fuel, it implodes under its own gravity, forming a region in space where gravity is so strong that nothing, not even light, can escape. This creates what we call a black hole, characterized by its event horizon, the boundary beyond which escape is impossible. They come in various sizes, ranging from stellar black holes, formed from single stars, to supermassive black holes, found at the centers of galaxies, containing millions or even billions of times the mass of our Sun. When two black holes orbit each other, they gradually lose energy through gravitational waves, ripples in space-time that travel outward from the merging bodies. Eventually, this energy loss causes them to spiral closer together, culminating in a merger. These collisions between black holes generate incredibly powerful gravitational waves, which can be detected from billions of light-years away, currently observed by facilities like LIGO and Virgo. The events triggered by these mergers offer an unparalleled opportunity to explore the universe's most extreme conditions. Significantly, black hole mergers can lead to several noteworthy cosmic events. For instance, they can influence star formation within their host galaxies and even affect the structure of those galaxies over time. The gravitational waves released during a merger can also contribute to our understanding of the universe's expansion rate and the fundamental laws of physics. Each detected merger adds a piece to the puzzle, allowing scientists to test theories about gravity, space-time, and the origins of black holes themselves. Furthermore, the study of black hole mergers opens up a world of discoveries regarding their role in the universe. As we continue to capture more of these monumental events, we gain insights into the history of galaxies and the evolution of the cosmos. It is a reminder that black holes, once thought to be mere curiosities, are dynamic players in the cosmic theater, shaping the universe in ways we are only just beginning to understand. Gravitational waves, often described as ripples in the fabric of space-time, are a fascinating and relatively recent discovery in the field of astrophysics. They are generated by dramatic cosmic events, such as the mergers of black holes. When two black holes spiral towards each other and eventually collide, they produce significant disturbances in the space-time around them, sending out gravitational waves that can travel across the universe. This phenomenon allows scientists to detect events that are otherwise invisible to traditional telescopes. By studying these gravitational waves, researchers can gather invaluable information about the characteristics of black holes. For example, the frequency and amplitude of the waves carry clues about the masses and spins of the merging black holes. Each merger provides a unique snapshot of the extreme environments surrounding these enigmatic objects. Since the first detection of gravitational waves in 2015, scientists have observed multiple events, gradually creating a library of information that enhances our understanding of black hole populations and their formation. Moreover, these waves offer insights into the early universe. As we detect and analyze more mergers, we can explore the conditions that existed in the cosmos billions of years ago. This research paints a clearer picture of how black holes evolve over time and the roles they play in cosmic structures. It also raises fascinating questions about the expansion of space and the behavior of gravity under extreme conditions, pushing the boundaries of our current theories. Furthermore, the study of gravitational waves opens the door to understanding fundamental physics. It might help resolve long-standing mysteries about dark matter, dark energy, and even the nature of gravity itself. As we continue to observe these cosmic events with advanced detectors, our grasp of the universe's deepest secrets will undoubtedly evolve, reminding us just how much there still is to learn about the cosmos in which we reside. Black hole mergers are some of the most fascinating events in the universe, and predicting when and where they occur combines advanced technology with deep cosmic understanding. Astronomers utilize gravitational wave detections as one of the primary tools for these predictions. Gravitational waves are ripples in spacetime produced by colossal events, such as when two black holes spiral towards each other and eventually collide. The Laser Interferometer Gravitational Wave Observatory, or LIGO, has been pivotal in observing these waves, giving scientists the ability to predict likely merger events based on previous occurrences. Another method involves studying the distribution of black holes in galaxies. By mapping out where black holes are concentrated, scientists can identify regions where mergers are more likely to occur. Generally, black holes are found in clusters, particularly within dense environments like globular clusters or the centers of galaxies. Assessing these dynamics helps researchers understand which black holes are more likely to come close enough to each other to eventually merge. The importance of these predictions extends beyond theoretical insights. They carry essential implications for our understanding of the universe. Predicting black hole mergers helps refine models of cosmic evolution, shedding light on how black holes interact and grow over time. Moreover, these mergers release enormous amounts of energy, and studying their frequencies and characteristics enhances our comprehension of gravity, space-time, and fundamental physics. Lastly, being able to predict these powerful cosmic phenomena opens doors for future observations and potential discoveries. Each merger provides unique data, allowing scientists to test and challenge existing theories about the structure of space-time and the nature of the universe. These efforts not only deepen our knowledge, but also inspire curiosity about the cosmos and our place within it. Predicting black hole mergers is not just about observing the past, it is about unlocking the mysteries that lie ahead. When black holes engage in a merger, the consequences ripple outward, affecting not only the black holes themselves, but also the surrounding star systems. The event itself releases an enormous amount of energy, predominantly in the form of gravitational waves. These waves are ripples in space-time caused by the accelerating masses of the merging black holes. Imagine the energy released as comparable to that of several solar masses being converted to energy in a fleeting moment, shaking the very fabric of space around them. The gravitational waves generated can have profound effects on nearby stars and stellar systems. As these waves propagate outward, they can influence the orbits of stars in proximity to the merging black holes. Stars may find their paths altered, potentially putting them on collision courses or ejecting them from their current orbit. This can lead to unstable systems, where some stars end up flung into the void of space, while others might be drawn closer to the black holes, increasing the chances of being consumed. In addition to gravitational disturbances, the merger might also influence star formation in the surrounding area. As black holes collide and release their energy, they may compress nearby gas and dust clouds, triggering bursts of star formation. This could create new stars over time, reshaping the neighborhood around the black holes. Conversely, the energy released might disrupt more delicate structures, preventing star formation in certain regions. Overall, the merger of black holes acts like a cosmic catalyst, altering the dynamics of the local stellar environment. This interplay between destruction and creation adds another layer of complexity to the life of a galaxy, demonstrating how interconnected the universe truly is. The effects of these mergers serve as a reminder of the dynamic and ever-evolving nature of the cosmos. As we look toward the future, technology is poised to significantly enhance our understanding of black hole mergers, those monumental cosmic events where two black holes spiral together and ultimately collide. For starters, advances in gravitational wave detectors will be at the forefront of this exploration. Instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, have already revolutionized our ability to observe these phenomena. As new detectors come online and existing ones are upgraded, we will gain increased sensitivity. This heightened ability will allow us to detect even more distant mergers, enabling scientists to gather a wealth of data that could lead to fresh insights into the nature of black holes. In addition to gravitational wave detection, the future holds great promise for electromagnetic observations. Next-generation observatories that can capture different wavelengths of light, from radio waves to gamma rays, will provide a multifaceted view of black hole mergers. By combining gravitational wave data with electromagnetic signals, known as multi-messenger astronomy, researchers will be able to piece together a more complete picture of these cosmic events. This integration of information will help illuminate the environments around black holes and further our understanding of their behavior just before and during mergers. Furthermore, advancements in computing technology will play a crucial role in analyzing the massive amounts of data generated from these observations. Deep learning and artificial intelligence are beginning to change how we interpret complex astronomical data. These tools can identify patterns and anomalies that might elude human researchers, allowing for more nuanced interpretations of black hole mergers. As algorithms improve, they will enhance our ability to model the dynamics of how black holes interact, leading to an understanding of their formation and evolution throughout the universe. Finally, international collaborations will create new opportunities to study black hole mergers at an unprecedented scale. Projects like the European Space-Based Gravitational Wave Observatory, LISA, have the potential to study black hole collisions in ways we've yet to imagine. The collaborative nature of modern science, combining efforts from institutions around the globe, will accelerate discoveries and refine our theoretical frameworks. With each technological advance, we step closer to unraveling the mysteries surrounding black holes, revealing the profound secrets of our universe. Stellar nurseries, often referred to as star-forming regions, are vast clouds of gas and dust in space where stars are born. These regions are rich in materials that fuel the birth process of stars. At the heart of these nurseries, the dense concentrations of gas and dust begin to collapse under their own gravity, leading to the formation of protostars. Over time, as these protostars gather material and heat up, they will ignite nuclear fusion, marking the birth of a new star. Understanding stellar nurseries is crucial to our comprehension of star formation because they provide the perfect environment for the complex processes involved. Within these regions, different elements come together in a delicate balance, allowing for various scenarios to unfold. The interaction between gravity, temperature, and pressure can lead to the formation of clusters of stars, which can vary in size and composition, illuminating the diversity of our universe. Furthermore, stellar nurseries often tell us about the life cycle of galaxies. When we study these regions, we gain insights into the history of star formation within our own Milky Way and other galaxies. Observing how often stars are born and their ultimate fate can reveal the patterns of galactic evolution over billions of years. This knowledge is foundational to cosmology, helping scientists piece together the story of the universe itself. In addition, stellar nurseries are often the sites of intense activity. The birth of new stars can ignite surrounding material, leading to phenomena such as stellar winds and supernovae. These explosive events can enrich the interstellar medium with heavier elements, further influencing subsequent generations of star formation. Therefore, by studying stellar nurseries, we not only learn about how stars are born, but also how they evolve and contribute to the cosmic cycle of matter. In the vastness of space, stellar nurseries, also known as molecular clouds, serve as the birthplaces of stars. These dense regions are filled with gas and dust where the conditions are just right for new stars to form. Gravity pulls this material together, causing clumps to form that gradually collapse. As they collapse, they spin and heat up, eventually igniting nuclear fusion at their cores. This process marks the true beginning of a star's life cycle, transforming simple atoms into heavier elements and releasing an incredible amount of energy. As stars form, they also influence their surroundings in remarkable ways. The intense energy emanating from newly born stars creates powerful stellar winds and radiation that can push away surrounding gas and dust. This interaction can trigger the formation of additional stars in the nursery, leading to many new generations of stars sprouting from the same cosmic cradle. These cosmic events illustrate how interconnected and dynamic a stellar nursery can be, as the birth of one star often paves the way for the birthing of many others. Beyond the formation of stars, these nurseries play a crucial role in the creation of planets. As stars develop, the remaining gas and dust can coalesce to form planetary systems. Within a spinning disk of material surrounding a young star, small grains of dust come together, forming larger clumps and eventually building up into planets. This disk may also have the right conditions for the accumulation of ice, rock, and gas, leading to a diverse range of planetary bodies. The life cycle of stars and planets within these cosmic events is not just a matter of creation, it's about the ongoing cycle of birth and death in the universe. When stars reach the end of their life cycles, particularly the massive ones, they often explode as supernovae, scattering their enriched materials back into the universe. This process enriches the interstellar medium with heavy elements and paves the way for new stars and planets to form, illustrating the beautiful continuity of cosmic evolution. Thus, stellar nurseries are not just places of beginnings. They symbolize the intricate tapestry of life, death, and rebirth in the cosmos. Exploring and documenting stellar nurseries is crucial for understanding the fundamental processes that lead to the formation of stars and planetary systems. Stellar nurseries are vast clouds of gas and dust, often found in regions of space known as molecular clouds. Within these environments, gravity pulls together this material, sparking nuclear fusion and giving birth to new stars. By studying these nurseries, scientists can learn about the life cycle of stars, including their birth, evolution, and eventual death. Despite their great distances from Earth, these regions hold secrets about the origins of our own solar system. The elements formed in stars are the building blocks of planets and life as we know it. By observing stellar nurseries, we gain insights into the conditions necessary for star formation, as well as the types of stars that emerge. This understanding can help us better predict the future of our solar system and the potential for life elsewhere in the universe. Moreover, technology has advanced to the point where we can capture detailed images and data from even the farthest nurseries. Instruments like powerful telescopes equipped with sensitive cameras and spectrometers allow astronomers to peer into these regions, observing phenomena like protostars and the intricate processes of accretion, those dramatic moments when gas and dust spiral into forming stars. This technological prowess makes it possible to gather evidence of how stars evolve over millions of years, despite the vast gulf of space that separates us. Lastly, as we explore stellar nurseries, we also tap into the grand narrative of the universe. Each discovery adds a piece to the puzzle of how galaxies evolve and interact. Understanding star formation helps scientists tell the story of the cosmos itself and illuminates the connection we share with the stars above us. Even though these nurseries are light years away, each revelation offers profound insights into our place within the universe and the cosmic phenomena that shape it. In the vast expanses of our universe, stellar nurseries, also known as molecular clouds, play a critical role in the birth of stars. These regions are dense with gas and dust, creating an environment rich in matter. Within these nurseries, gravity begins to take the lead. As areas of gas and dust accumulate, they start to collapse under their own weight, resulting in the formation of protostars. This process is not just significant for individual stars, rather, it sets the stage for the evolution of galaxies and consequently the cosmos itself. As protostars form, they generate enormous amounts of energy, primarily through nuclear fusion when they finally ignite. This energy expels powerful stellar winds, sculpting the surrounding gas and dust into intricate and beautiful structures. This phenomenon can lead to the creation of nebulae, where new stars, planets, and even rich organic materials begin to emerge. It is a creative cycle that continually shapes our universe, influencing not only the stars that will someday shine, but the very fabric of the galaxies in which they reside. Moreover, some of the energetic events occurring in stellar nurseries can trigger a cascade of star formation. When massive stars reach the end of their lives, they can explode in a supernova, blasting shockwaves through nearby regions of the molecular cloud. This dynamic can compress nearby gas, igniting the birth of new stars in a process called triggered star formation. Such events have ripple effects throughout the galaxy, enhancing its complexity and diversity. Ultimately, the phenomena occurring within stellar nurseries are essential for cosmic evolution. They set the stage for the formation of not just individual stars, but also stellar systems, planetary bodies, and potentially life itself. By understanding these dynamic environments, we gain insight into the broader processes shaping our universe and the ongoing story of creation that unfolds within it. Scientists have developed a sophisticated understanding of how and where massive stars form, primarily through observations and simulations of cosmic environments. Massive stars typically emerge in regions rich with gas and dust, known as molecular clouds. These clouds serve as cosmic nurseries, where gravity pulls together gas and dust, causing regions to become denser. Eventually, these regions collapse under their own weight, igniting the stellar birth process. To predict how and when massive stars form, scientists employ a variety of observational techniques. They use powerful telescopes that can peer through the dense clouds of gas and dust. By observing infrared and radio wavelengths, which can penetrate the obscuring materials, researchers can map out the structure, temperature, and density of these clouds. This data helps them identify the locations with the highest potential for star formation. In addition to observational methods, scientists utilize computer simulations of molecular cloud dynamics. These simulations take into account various factors such as turbulence, magnetic fields, and the influences of nearby stars and other cosmic phenomena. By manipulating these variables, researchers can model how dense regions evolve over time, allowing them to predict where massive stars are likely to form in the future. Another critical factor in understanding star formation is the abundance of elements within these regions. Massive stars are born in environments that have a significant amount of hydrogen and helium, but secondary generations can form in clouds enriched by the remnants of earlier supernova. This ongoing cycle of star death and birth plays an essential role in determining where the next generation of stars will rise. Through this intricate interplay of observations, simulations, and chemical composition, scientists can piece together the cosmic puzzle of massive star formation. The transformation of the Sun into a red giant marks a significant milestone in the life of our solar system, and it will profoundly alter the environment surrounding it. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to fuse helium. As this process unfolds, the Sun will expand enormously, potentially swelling to a diameter that reaches the orbit of Earth and possibly beyond. This expansion means that the inner planets, including Mercury and Venus, will be engulfed by the fiery mass of the Sun. For Earth, the impact will be catastrophic. As the Sun grows in size and brightness, the temperatures on our planet will rise dramatically. This intense heat will likely boil away the oceans, stripping Earth of the conditions necessary for life as we know it. It won't just be a gradual warming. The climate and the very nature of the planet will shift in a matter of just a few million years. Similarly, any remnants of our atmosphere could be blown away, leaving behind a barren landscape. The outer planets and their moons may also experience significant changes due to the Sun's evolution. For instance, the gravitational influence of the Sun will remain, but the dramatic changes in temperature and radiation will affect the atmospheres and potential habitability of the gas giants and their icy moons. Some distant objects in the solar system, like the Kuiper Belt, may become more stable as the gravitational pull of a swollen sun alters their orbits, leading to a new dynamic in the outer regions of the solar system. This transformation is a natural phase for stars like ours, yet it serves as a poignant reminder of the impermanence of celestial bodies. While life as we know it on Earth will come to an end, this cosmic event will also pave the way for new possibilities in the universe, leaving behind remnants that could one day form new stars and planets. The cycle of creation and destruction continues, a poignant illustration of nature's enduring and ever-evolving tapestry. Studying the Sun's life cycle is essential not only for understanding our own star, but also for gaining insight into cosmic events that shape the universe. The Sun, like other stars, goes through a series of evolutionary stages ranging from its formation to its eventual demise. By comprehending this process, we can better grasp the life cycles of other stars in the universe, which share similar patterns and characteristics. The Sun's life cycle consists of several important phases, beginning with the nuclear fusion of hydrogen in its core. Throughout billions of years, it gradually transforms into a red giant, shedding its outer layers and leaving behind a dense core known as a white dwarf. This transformation has implications far beyond our solar system. When stars like the Sun evolve, they enrich their surroundings with heavy elements, providing the building blocks necessary for planets and life forms, including our own Earth. Moreover, the Sun plays a critical role in cosmic events that affect the entire solar system. Its activities, such as solar flares and sunspots, can influence the space weather around Earth. These bursts of energy can disrupt communications, affect satellite operations, and even pose risks to astronauts in space. Understanding our Sun's behavior contributes to our ability to predict these phenomena, which is vital for maintaining modern technology and ensuring safety. Finally, the Sun's eventual fate serves as a critical reminder of the dynamic nature of the universe. The life cycle of our star is not only a reflection of its own existence, but also a key to understanding the larger cosmic story. By studying our Sun, we unlock the mysteries of stellar evolution, the formation of planetary systems, and the very essence of the elements that make up everything we know. This knowledge fuels our curiosity and deepens our appreciation for the intricate web of life and energy in the cosmos. The Sun, our closest star, offers a unique window into the life cycles of stars across the universe. Understanding its evolution helps astronomers piece together the bigger picture of stellar development. The Sun is currently classified as a middle-aged star, roughly halfway through its lifespan of about 10 billion years. Through careful observation and study, scientists have charted its past and predicted its future, serving as a typical example for similar stars. As the Sun ages, it will follow a well-documented path of evolution that mirrors that of other stars in its class, known as G-type stars. It began as a dense cloud of gas and dust, ultimately igniting nuclear fusion in its core. Over the next few billion years, it will steadily burn hydrogen, during which time it will gradually swell into a red giant. This transition not only illustrates the life cycle of the Sun, but also helps us understand the fates of countless stars that follow similar patterns. The end stage of the Sun's life is particularly telling. Once it exhausts its hydrogen fuel, it will, after a brief period of instability, shed its outer layers, creating a beautiful nebula while leaving behind a dense core known as a white dwarf. By studying the Sun's transformation into a white dwarf, we gain crucial insights into the eventual outcomes for many stars, including those that are larger and smaller than the Sun. Moreover, by comparing the Sun's life cycle with other stars, astronomers can infer key factors like metallicity, mass, and temperature, which influence the evolutionary paths of different types of stars. These insights enrich our understanding of stellar populations in various environments throughout the universe, highlighting the intricate workings of astrophysical processes. Thus, the Sun not only illuminates our sky, but also illuminates the broader narrative of stellar evolution. The transformation of the Sun into a red giant is a profound event that will have dire consequences for our planet, Earth. This stage in the Sun's life cycle, expected to occur in about 5 billion years, follows its transition through the main sequence phase, where it has spent the bulk of its life burning hydrogen. As the Sun exhausts its hydrogen fuel, it will begin fusing helium, causing it to expand significantly. This expansion will drastically increase its size, potentially engulfing the inner planets, including Mercury and Venus, and putting Earth at severe risk. If Earth remains intact as the Sun swells, the rising temperatures would render our planet inhospitable. Surface temperatures could soar to levels that would lead to the complete evaporation of oceans and a collapse of the ecological systems that support life. Even if Earth escapes being engulfed, the intense heat from the expanding Sun would strip away the atmosphere, leaving behind a barren rock devoid of life. The conditions necessary for maintaining water and life as we know it would disappear, fundamentally altering the planet. Further consequences would unfold as the Sun sheds its outer layers and enters the later stages of its life cycle. The solar winds and increased radiation would not only pose dangers to any remaining life, but could also disrupt the orbital paths of planets and other celestial bodies in the solar system. This could create a chaotic environment that might lead to collisions or other unforeseen consequences for the remnants of our planetary system. However, in the grander scheme of the universe, the transformation of the Sun into a red giant is a natural part of stellar evolution. The materials expelled by the dying star will enrich the interstellar medium, providing the building blocks for new stars and potentially new planetary systems. While the changes brought on by the Sun's transformation spell the end of Earth as we know it, they also highlight a cosmic cycle of destruction and renewal that has been a fundamental aspect of the universe for billions of years. To understand how scientists simulate the future of the Sun, we first need to appreciate its incredible life cycle. The Sun is a middle-aged star, about 4.6 billion years old, and scientists predict it has about 5 billion years left before it exhausts its nuclear fuel. Given this expansive timeline, astronomers employ sophisticated modeling techniques to project what will happen to the Sun as it ages. Central to these simulations is the application of mathematical models that describe the Sun's structure and processes. These models take into account the balance of forces within the Sun, especially the gravitational pull that seeks to collapse it, and the outward pressure from nuclear fusion that works to expand it. By varying conditions in their models, scientists can simulate different stages of the Sun's life, including its transition to a red giant, where it will expand vastly and possibly engulf the inner planets, including Earth. In addition to those fundamental forces, these simulations incorporate physics surrounding energy generation through nuclear fusion. By including factors such as temperature, pressure, and the composition of the Sun's core, researchers simulate how these elements change over time. They can predict how the fusion of hydrogen into helium will cease as the Sun's hydrogen fuel is depleted, paving the way for helium fusion and the subsequent stages of stellar evolution. As the models evolve, they also consider external influences, like the interaction with solar winds and the effect of stellar activity on surrounding space. These detailed simulations not only help us understand the Sun's future, but also provide insights into the life cycles of other stars in the universe, enriching our comprehension of stellar evolution. Thus, through advanced calculations and an understanding of fundamental physics, scientists paint a detailed picture of our Sun's aging process, revealing fascinating insights about our cosmic neighborhood and its future. As we gaze into the vastness of the cosmos, we're reminded that the universe's story is not just about its creation, but also about its eventual fate. Scientists have developed several theories regarding what is often called the death of the universe, each one provoking our thoughts about the ultimate end of everything we know. One prevailing theory is known as the Big Freeze. In this scenario, the universe continues to expand forever. As it does, galaxies will drift further apart and stars will burn out, leaving behind a dark and cold cosmos. Eventually, this chilling scenario leads to a point where stars no longer form, and even the remnants of stars and galaxies decay away, resulting in a universe filled with only low-energy particles. It's a rather chilling prospect, one where the universe becomes increasingly empty and desolate over an unfathomable timescale. Contrasting this idea is the Big Crunch scenario. According to this theory, the expansion of the universe might reverse if the total density of the universe is sufficient to overcome its expansion. If this is the case, the universe could stop expanding and begin to collapse back on itself. This would cause galaxies to draw ever closer until they ultimately crash together, leading to a singularity, a point where the laws of physics, as we currently understand them, cease to apply. While this theory seems almost poetic in its cyclic nature, it hinges on yet-to-be-determined properties of dark energy and matter. Then we have the more recent consideration of the Big Rip. In this wild hypothesis, the universe's expansion may not just continue, but accelerate exponentially. If the force driving this acceleration, associated with dark energy, grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. Such an outcome presents a universe where everything is ripped apart, highlighting our fundamental lack of control over cosmic forces. Each of these theories invites us to wonder, revealing not just the fragility of our own existence, but the extremes of the universe itself. Understanding these possibilities is less about accepting a single fate and more about appreciating the intricate, ever-changing dance of cosmic forces that governs all existence. As we look up at the night sky, we are reminded of the vast cosmic tapestry in which our universe exists. Right now, we observe celestial events influenced by the presence of stars, galaxies, and various astronomical phenomena that interact with one another in countless ways. However, as the universe ages and evolves, the tapestry will change dramatically, particularly at its very end, leading to cosmic events that will be unrecognizable compared to what we know today. In the distant future, the universe is expected to experience a phase where star formation gradually halts. Stars will exhaust their nuclear fuel and die out, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Over vast timescales, these remnants will cool and fade, leading to a dark and quiet universe. Instead of the bright spectacle of stars twinkling overhead, future observers, if any exist, will witness a cold, empty void punctuated only by the faint glow of long dormant stars. Moreover, the expansion of the universe is predicted to continue accelerating. This means that distant galaxies will drift farther away from us and from each other, eventually becoming unreachable and unobservable. The light from these galaxies will redshift beyond visibility, rendering them invisible to any observers set amidst a dark cosmos. This vast isolation will fundamentally alter the landscape of cosmic events, rendering the spectacular collisions and interactions we currently observe as mere memories of a vibrant universe. At the very end stages, cosmic events will focus on processes like the merging of black holes and the occasional collision of stellar remnants. These events will be rare and happen in a universe that feels mostly abandoned. The echoes of a vibrant past will remain, embodied in grassy remnant starlight, but the universe itself will transform into a serene and desolate realm of features and phenomena that starkly contrast the rich dynamic activities we see today. Thus, the end of the universe promises to be a silent, shadowy finale, a far cry from the bustling realm of stars and galaxies we currently call home. The concept of the heat death of the universe offers a profound perspective on cosmic evolution, marking a potential end state where the universe reaches maximum entropy. Entropy is a measure of disorder, and as it increases, energy becomes more evenly distributed. In this scenario, stars exhaust their nuclear fuel, galaxies drift apart, and the universe becomes a cold, dark expanse. Understanding this eventual fate allows scientists to grasp the long-term trends in cosmic evolution and the inevitable changes that will shape the future. This idea also emphasizes the dynamic nature of the universe. Initially, much of cosmic history is characterized by structures forming, stars igniting, galaxies colliding, and planets emerging. As time progresses, however, energy sources diminish, and the universe becomes less hospitable to life as we know it. This gradual decline serves as a reminder of the balance in cosmic forces, where the birth of new entities is always intertwined with an eventual cycle of decay and transformation. The significance of heat death extends beyond physical realities. It stirs deep philosophical reflections on the nature of existence. For ages, humanity has gazed up at the stars, contemplating our place in the cosmos. The concept of an ultimate end, where everything fades into uniformity, challenges us to think about time and the legacy of our existence against the backdrop of an ever-evolving universe. What does it mean to be born, to thrive, and then to fade into the void? Moreover, considering heat death reshapes our understanding of time itself. Traditionally, we perceive time as a linear progression, but the potential for a heat death introduces a cosmic timeline that might transform all events into a single end point. That notion evokes fascination and dread, presenting an intriguing paradox. From the energetic moments of the Big Bang to the quiet stillness of future cosmic solitude, the universe tells a story of creation and, ultimately, the silence of entropy. Each phase of cosmic evolution reveals not only the physical laws at play, but also our enduring quest for meaning within this vast, ever-changing cosmos. The various scenarios regarding the end of the universe carry significant implications for future researchers, shaping not only their understanding of cosmic evolution, but also the direction of scientific inquiry and technological advancement. Each potential outcome, whether it be the Big Freeze, the Big Crunch, or the Big Rip, offers distinct challenges and questions that demand exploration. For instance, if the universe is indeed heading towards a Big Freeze, researchers may focus their efforts on understanding how galaxies evolve in an ever-expanding space, where stars gradually burn out and the cosmic landscape is increasingly isolated. On the other side, if the universe is destined for a Big Crunch, where it ultimately collapses back on itself, this scenario could direct inquiry towards studying gravitational forces and space-time physics. Such understanding could lead to revolutionary discoveries about the fundamental nature of space, time, and gravity. The potential for a cyclic universe, where it expands and contracts repeatedly, could drive researchers to investigate not just the physical processes involved, but also the origins and fate of cosmic structures over eons. Additionally, the Big Rip presents a stark, almost dramatic outcome, where the universe's expansion continues to accelerate until galaxies, stars, and even atoms are torn apart. This raises profound questions about the stability of the laws of physics and the nature of dark energy, encouraging researchers to explore these enigmatic forces more deeply. Unraveling the mysteries of dark energy might even pave the way for groundbreaking technologies or materials that could alter our understanding of physics and the cosmos altogether. The end of the universe is not merely an esoteric concern. It impacts how we approach the fundamental questions of life, existence, and our place in the cosmos. These scenarios invite researchers to not only contemplate what lies ahead, but also inspire new generations to look upward and explore the universe's many mysteries, fueling innovation and discovery in ways we can barely imagine. Advancements in technology play a pivotal role in unraveling the mysteries of the universe's ultimate fate. With each new technological breakthrough, we gain sharper tools and techniques that expand our observational capabilities and improve our theoretical models. For instance, telescopes equipped with advanced sensors now allow astronomers to detect light from the most distant galaxies, offering insights into the universe's early days and its expansion over billions of years. One significant area where technology has made strides is in the development of gravitational wave detectors. These sophisticated instruments can sense minute ripples in space-time caused by cosmic events, such as the collision of black holes. By studying these waves, scientists can gain unique information about the behaviors and properties of such extreme phenomena, which can improve our understanding of broader cosmic truths and the endpoints of stellar evolution. Additionally, powerful supercomputers enable researchers to simulate complex cosmic phenomena with remarkable accuracy. These simulations allow scientists to test various theories about the fate of the universe, from the Big Crunch, where all matter collapses back, to the Big Freeze, where the universe continues to expand and cool indefinitely. Through rigorous computational modeling, we can explore scenarios that may otherwise be impossible to observe directly. Lastly, innovations in artificial intelligence and machine learning are beginning to transform data analysis processes. These technologies help sift through large volumes of astronomical data, identifying patterns and insights that human researchers might miss. As we leverage these advancements, our understanding of the universe's fate becomes clearer, revealing the intricate tapestry of cosmic events that shape our existence. With each step forward, we unlock a deeper appreciation for the universe we inhabit and its intriguing, evolving future. Gamma-ray bursts are among the most powerful explosions in the universe, releasing immense amounts of energy in a very short time. They can last from just a fraction of a second to several minutes and are visible across vast distances. These cosmic bursts often outshine entire galaxies for brief periods, making them some of the brightest events we can observe from Earth. They are thought to occur during massive stellar explosions, such as supernovae or the collapse of massive stars into black holes. While gamma-ray bursts are extraordinarily intense, they are relatively rare in the grand scheme of cosmic events. Astronomers estimate that we might see anywhere from 1 to 3 gamma-ray bursts in our vicinity each century. However, in the universe as a whole, they occur much more frequently. It's estimated that a gamma-ray burst happens somewhere in the observable universe roughly once every 10,000 years per galaxy. Given the billions of galaxies scattered throughout the cosmos, this means they are happening quite frequently on a cosmic scale. One of the most intriguing aspects of gamma-ray bursts is their directional nature. These bursts are not spherical but are instead emitted in narrow jets. If Earth happens to be in the path of one of these jets, the effects can be devastating, although the likelihood is exceedingly low. Fortunately for us, the nearest known gamma-ray bursts have occurred thousands of light-years away, posing no threat to our planet. Gamma-ray bursts continue to be a focal point of astronomical research, enhancing our understanding of the life cycle of stars, the formation of black holes, and the very nature of the universe itself. Each time astronomers detect a burst, they gain invaluable insights into the processes that govern our cosmos, further illuminating the mysteries of stellar evolution and the extreme environments that exist beyond our world. Gamma-ray bursts are among the most energetic events in the universe, unleashing enormous amounts of energy in a fraction of a second. If one were to occur relatively close to Earth, within a few thousand light-years, it could have devastating consequences for our planet. The radiation from such an explosion could strip away the ozone layer, which protects us from harmful ultraviolet radiation from the sun. Without this protective shield, life on Earth would be exposed to increased levels of radiation, which could lead to significant ecological disruptions and health risks for living organisms. Moreover, the immense energy released during a gamma-ray burst can cause atmospheric chemistry changes. As ozone levels drop, the sun's intense ultraviolet rays could lead to a rise in skin cancers and cataracts in humans, as well as disrupting the delicate balance of ecosystems. Many plant species would struggle to survive, affecting the entire food chain. With reduced plant life, herbivores would find it difficult to feed, which would inevitably impact carnivores as well. The consequences could ripple through various biological systems and further diminish biodiversity on Earth. Interestingly, while the theoretical impacts of a nearby gamma-ray burst sound catastrophic, the likelihood of such an event occurring close enough to Earth to cause harm is extremely low. In fact, there haven't been any recorded gamma-ray bursts within a critical threshold that would seriously threaten life as we know it. Fortunately for us, our planet is situated in a relatively safe region of the Milky Way galaxy, far from the potential hazards of supernovae and gamma-ray burst sources. Nonetheless, the idea of gamma-ray bursts adds to our understanding of cosmic events and their potential impacts on Earth. They serve as a reminder of the dynamic and sometimes dangerous universe we inhabit. Overall, while the risk remains minimal, gamma-ray bursts remain a fascinating topic in the study of cosmology and the evolution of life on Earth. Gamma-ray bursts, the most powerful explosions in the universe, have intrigued scientists for decades. These cosmic events are short-lived, emitting intense bursts of gamma radiation that can outshine entire galaxies for a brief moment. To better understand these enigmatic phenomena and possibly predict their occurrence, researchers are employing several advanced strategies and technologies. One of the key developments in this field is the use of space-based observatories. Instruments like the Fermi Gamma Ray Space Telescope continuously survey the sky, detecting gamma rays and cataloging bursts as they happen. This telescope specializes in identifying the afterglow of these events across various wavelengths, enhancing our understanding of their origins and the conditions under which they occur. Scientists are also collaborating on projects that involve ground-based observatories, using them in conjunction with satellite data. By coordinating ground telescopes to focus on regions of space where a gamma-ray burst is detected, researchers can gather vital information on what happens after the initial explosion. This multifaceted approach improves the chances of locating and studying these bursts while they are still bright and accessible. In addition to observational studies, theoretical research plays a huge role in predicting gamma-ray bursts. Scientists are creating models of massive stars and their explosive end stages, enabling them to forecast where and when these bursts might occur. By merging observational data with theoretical predictions, we are taking promising steps toward not only locating gamma-ray bursts in the future, but also unraveling the mysteries behind one of the universe's most fascinating spectacles. Gamma-ray bursts are one of the most mysterious phenomena in the universe. They release staggering amounts of energy in a fraction of a second, often outshining entire galaxies. The challenge of pinpointing their origins stems from the extreme distances at which they occur and the brief, fleeting nature of their emissions. These bursts can last anywhere from a fraction of a second to several minutes, far too quick for observatories to get a complete picture in real time. To complicate matters further, gamma-ray bursts are not limited to a single cause. They can result from various cosmic events, including the collapse of massive stars into black holes or the merging of neutron stars. Each type of event has its distinctive characteristics. For example, long-duration bursts are typically linked to the deaths of massive stars, while short-duration bursts often arise from the collision of compact objects like neutron stars. The diversity in origins makes it difficult for scientists to develop a unified theory explaining all gamma-ray bursts. Once a gamma-ray burst is detected, astronomers race against the clock. They use satellites and ground-based telescopes to monitor the afterglow, which can be visible across multiple wavelengths, including visible light and radio waves. This afterglow can provide valuable clues about the explosion's distance and physical properties. However, because these bursts are so distant, the light they emit may have traveled billions of years to reach us, meaning they might occur in different cosmic conditions than those we can observe today. While astronomers have made significant strides in understanding gamma-ray bursts, the quest to fully unravel their origins continues. Each discovery adds another layer to our understanding of the universe, revealing the violent processes that shape galaxies and stars. With each new observation, scientists are hopeful of uncovering more about these enigmatic bursts, peeling back layers of mystery and offering deeper insights into the cosmos we inhabit. Gamma-ray bursts are among the most powerful explosions in the universe, emitting immense amounts of energy in an extremely short time. They can release more energy in a few seconds than our sun will emit throughout its entire lifetime. Understanding these bursts provides invaluable insights into the life cycle of the universe, especially regarding the formation of massive stars and the catastrophic events that end their lives. When a massive star exhausts its nuclear fuel, it may collapse into a black hole. This process can trigger a gamma-ray burst, making these events strong indicators of stellar death. By studying gamma-ray bursts, astronomers can gather information about the conditions surrounding dying stars, contributing to our knowledge of stellar evolution and the processes that lead to black hole formation. Each burst is like a beacon, illuminating regions of the universe where massive stars have lived and died. Moreover, gamma-ray bursts are not only significant in cosmic evolution, they also play a crucial role in understanding the expansion of the universe. When we observe these bursts from distant galaxies, we are essentially looking back in time. Their light takes billions of years to reach us, allowing scientists to study the early universe during periods that are otherwise obscured by cosmic dust and gas. This can help refine our models about how fast the universe is expanding and its overall structure and composition over time. Additionally, the isotopic elements produced in the violent explosions of gamma-ray bursts might contribute to the cosmic abundance of heavy elements. This connects to the broader narrative of the universe's life cycle, from the Big Bang to the formation of stars and galaxies. By piecing together these cosmic puzzles, researchers continue to deepen our understanding of how the universe evolves and transforms, revealing the intricate connections between the death of stars and the birth of new phenomena. Monitoring near-Earth objects, commonly known as NEOs, is a crucial aspect of planetary defense. These space rocks, which include asteroids and comets with orbits that bring them close to Earth, can pose a significant threat if their paths intersect with our planet. Understanding the size, composition, and trajectory of these objects allows scientists to assess the potential risk they might pose to us. One of the most compelling reasons for tracking NEOs is the potential for catastrophic impacts. History shows us that even relatively small objects can cause extensive damage. For instance, the event in 2013 where a meteor exploded over Chelyabinsk, Russia, injured over 1,000 people and damaged thousands of buildings. Such incidents serve as stark reminders that NEOs are not just distant threats, they are real and can affect us directly. By continually monitoring the skies, astronomers can detect NEOs early, providing the opportunity to strategize for possible deflection or evacuation if a significant threat is identified. Various methods are explored, such as nuclear devices or kinetic impactors, to change the trajectory of an oncoming asteroid. This proactive approach makes it possible to avert a potential disaster before it becomes imminent. Furthermore, studies of NEOs are not just about self-defense, they also enhance our understanding of the early solar system. These objects are considered remnants from its formation, offering insights into the building blocks of planets. Therefore, by monitoring and studying NEOs, scientists engage not only in safeguarding our planet, but also in unraveling the mysteries of our cosmic origins. Scientists employ a multifaceted approach to assess the risks posed by asteroids and comets to our planet. The journey starts with detecting these celestial objects. A variety of ground-based telescopes and space missions continuously scan the skies for near-Earth objects, or NEOs, which include asteroids and comets that come within 130 million kilometers of our planet. By measuring the light they reflect and studying their movements, scientists can determine their size, shape, and orbit. Once a NEO is detected, researchers analyze its trajectory to predict whether it might eventually collide with Earth. This process involves sophisticated computer modeling that factors in gravitational influences from other celestial bodies, as well as the Yarkovsky effect, can slightly alter its orbit over time. These models help create a long-term risk assessment, allowing scientists to gauge probabilities of potential impacts. In addition to orbital predictions, scientists assess the physical characteristics of these objects. Understanding their composition is crucial, as it influences how likely they are to survive an atmosphere entry and what kind of damage they might cause if they do collide with Earth. For example, a metallic asteroid could cause much different damage compared to a porous, icy comet, which might disintegrate in our atmosphere. Moreover, ongoing international collaboration and data sharing enhance our ability to identify and track objects that could pose a danger. Programs and observatories around the world work together to refine their detection methods, share vital information, and develop potential deflection strategies for high-risk objects. This impressive network empowers humanity to remain vigilant and prepared, ensuring that we understand and can respond to the cosmic threats that lurk beyond our atmosphere. A major asteroid impact on Earth could significantly alter the course of life in profound ways. The sudden arrival of such a celestial body would unleash an enormous amount of energy. This explosive force would create widespread destruction in the immediate vicinity, obliterating entire ecosystems and leading to the extinction of many species. Yet, the effects would ripple far beyond the initial impact site. After the impact, vast clouds of dust and debris would be propelled into the atmosphere, blocking sunlight for extended periods. This phenomenon, often referred to as impact winter, would dramatically lower surface temperatures, disrupting photosynthesis on a global scale. Without sunlight, plants would struggle to survive, leading to collapses in food chains. Herbivores would find their food scarce, leading to declines in their populations, which in turn would affect the carnivores dependent on them. In addition to temperature changes, the impact could trigger wildfires and massive tsunamis, changing landscapes and creating new barriers for wildlife. The combination of these catastrophic events could lead to mass extinctions, similar to what is thought to have occurred around 66 million years ago when a large asteroid struck Earth and is widely believed to have caused the downfall of the dinosaurs. This event reshaped the course of evolution, allowing for the rise of mammals and eventually the appearance of humans. Life that does manage to survive such an event would be forced to adapt to new conditions. This could spur rapid evolution and diversification, as organisms that endure the harsh environments might evolve into new niches. The aftermath of an asteroid impact could usher in a new era of biological innovation, altering the trajectory of life on our planet in unexpected and astonishing ways. The legacy of an asteroid strike, therefore, is not just destruction, but also the potential for renewal and change. As humanity grows ever more aware of the potential dangers from space, scientists and researchers are hard at work devising strategies to mitigate the risks posed by asteroids and comets. One of the most prominent initiatives involves identifying and tracking near-Earth objects, which are celestial bodies that can come close to Earth's orbit. Various organizations like NASA and the European Space Agency consistently scan the skies using powerful telescopes. They search for these objects to better understand their paths and predict any that may pose a threat. In addition to keeping an eye on the skies, researchers are actively developing technologies to divert or alter the course of these hazardous objects. One of the fascinating concepts being explored is the gravity tractor. This method involves placing a spacecraft close to an asteroid, leveraging its gravitational pull over time to gently nudge the asteroid off its collision course. Another prominent undertaking is the Double Asteroid Redirection Test, or DART, which aims to demonstrate how a kinetic impactor could change an asteroid's trajectory by crashing into it at high speed. The results of such experiments could provide invaluable data on our capabilities to handle future threats. Furthermore, international collaboration is becoming increasingly vital in this fight against cosmic dangers. Countries and organizations are pooling resources and information to create a more unified response to potential threats. This includes sharing observational data, developing emergency response protocols, and coming together to form comprehensive strategies. The notion of a global asteroid defense system is no longer just a fantasy. It is being discussed as a serious possibility for the future. While we have much work ahead of us, these combined efforts signify a growing recognition of humanity's responsibility to safeguard our planet from the unpredictable nature of space. The initiatives in tracking, technology development, and global cooperation highlight a proactive approach to a potential existential threat, ensuring that we are better prepared for whatever may come our way. This awareness and preparedness set the stage for a more secure future, as we continue to explore the mysteries of our universe. Asteroid impacts have played a significant role in shaping our planet's history, with some events leading to major changes in Earth's environment and biological life. By studying historical asteroid impacts, scientists can develop models to understand the frequency, size, and potential effects of future threats. This research is critical because it enables us to anticipate and possibly mitigate the consequences of similar events in the future. One of the most famous examples is the impact event that occurred around 65 million years ago, which is widely believed to have contributed to the extinction of the dinosaurs. By analyzing the crater left by this asteroid, researchers can gather data on the impact's size and speed, as well as the energy released upon collision. Such historical examples offer invaluable lessons on the possible consequences of future impacts, guiding scientists to classify asteroids based on their likelihood of coming close to Earth. Furthermore, scientists utilize findings from past events to improve their detection methods for potentially hazardous asteroids. The data gathered from craters, the distribution of impact debris, and other geological evidence provide clues about the trajectory and velocity of these cosmic rocks. By employing advanced technology and computer simulations, researchers can better predict the orbits of asteroids and assess which might pose a threat to our planet. In addition to enhancing our predictive capabilities, studying these historical events raises public awareness about the importance of monitoring near-Earth objects. Understanding our planetary history helps shine a light on the need for vigilance, as there is still much we don't know. By examining the past, we equip ourselves to safeguard our future against potential asteroid impacts, ensuring we are prepared should a similar event occur. When we talk about the cosmic horizon in astronomy, we are referring to a boundary that defines the limits of what we can see in the universe. This horizon is not a physical barrier, but a result of the finite speed of light and the vast distances between celestial objects. Essentially, it marks the edge of the observable universe, creating a dome around us where the light emitted from distant galaxies has had just enough time to reach Earth since the universe began. Imagine the universe as a large balloon being inflated. As it expands, the surface of the balloon represents space, and the points on it signify galaxies. The cosmic horizon can be thought of as the farthest point you can see on that balloon's surface. Beyond this horizon, light from those distant regions has not yet reached us, so we cannot observe them directly. The light we see from the edge of our cosmic horizon comes from the very first moments, just around 380,000 years after the Big Bang. The distance to this cosmic horizon is staggering. It's over 46 billion light-years away. This means that when we look out into space, we are looking back in time, seeing light that has traveled for billions of years to finally reach us. As we explore the universe using advanced telescopes, we continue to push the boundaries of this horizon, discovering new galaxies, stars, and phenomena that deepen our understanding of cosmic history. As we ponder the cosmic horizon, we can also reflect on its implications for our understanding of the universe. What exists beyond it remains a mystery, opening up questions about the structure and fate of the cosmos. This boundary invites us to imagine not just the universe we can observe, but also the vast, possibly infinite regions that lie beyond our reach, forever tantalizing our scientific curiosity. The cosmic horizon represents the boundary of what we can observe in the universe. This limit is not just a simple line. It's influenced by the finite speed of light and the age of the universe itself. Light from the most distant objects can take billions of years to reach us. Hence, the farther we look, the more ancient the light we are seeing. In this context, studying the cosmic horizon helps us understand the limitations of our observable universe and the potential mysteries that lie beyond it. By examining the cosmic horizon, scientists gain insight into the nature of the universe's expansion. The universe has been expanding since the Big Bang, and as it continues to expand, light from distant galaxies is stretched, which we call redshift. This phenomenon informs us about the rate at which the universe is growing and helps us uncover the properties of dark energy, a mysterious force that drives this accelerated expansion. Understanding this cosmic horizon, therefore, is pivotal to sketching a complete picture of our universe. Moreover, working within the bounds of our observable universe compels scientists to confront crucial questions about what lies beyond. If there is more universe outside our cosmic horizon, what does it look like? Is it similar to what we see, or is it fundamentally different? These questions open the door to exciting theories, including ideas that propose the possibility of multiverses or regions of space that operate under different physical laws. The study of the cosmic horizon is vital not just for acknowledging our observational limits, but also for broadening our understanding of the cosmos. It challenges the scientific community to be innovative, to think beyond direct observation, and to uncover the deeper truths about existence and the fundamental workings of reality itself. The cosmic horizon marks the limit of what we can observe in our universe, dictated by the finite speed of light and the vast distances between objects in space. Beyond this horizon lies a realm that remains largely unknown, a domain that sparks the imagination of astronomers and cosmologists alike. There are a few intriguing possibilities that could expand our understanding of this mysterious territory. Firstly, advancements in technology and observational methods might allow us to gather data from even farther reaches of the cosmos. Innovations in telescopes, such as those planned for the James Webb Space Telescope and its successors, are designed to detect light from the earliest galaxies formed after the Big Bang. This not only helps us peek into the distant universe, but may also provide clues about its expansion and the potential existence of structures or phenomena hidden beyond our current observational capabilities. Another tantalizing concept is the idea of cosmic inflation, which theorizes that the universe underwent an exponential expansion in its infancy. If variations in the inflationary process have occurred, they could hint at other bubble universes beyond our own, with potentially different physical laws or constants. This theory suggests that our universe might be just one of many in a vast multiverse, each with unique characteristics. Such ideas push the boundaries of our understanding and compel us to consider the universe in a broader context. Lastly, the exploration of gravitational waves and dark matter could unlock secrets about the fabric of reality itself. By studying cosmic events, such as the collision of black holes or neutron stars, we can glean information about regions beyond our view. Gravitational waves have the potential to reveal phenomena that light cannot reach, offering a fresh perspective on parts of the universe obscured from our sight. As we tread deeper into these avenues of inquiry, we may find ourselves not just answering questions, but also unveiling new realms of fascination that redefine our comprehension of the cosmos. As we look into the future, cosmic events promise to reshape our understanding of the universe's boundaries in profound ways. One of the most significant occurrences on the horizon is the eventual collision of our Milky Way galaxy with the Andromeda galaxy. This merger, set to happen in approximately 4 billion years, will not only alter the structure of our own galaxy, but will also challenge our notions of galactic boundaries. When these two massive collections of stars interact, their stars will shift positions and new stellar neighborhoods will form. This event serves as a reminder that boundaries in the universe are not fixed, but are dynamic, continually reshaped by gravitational forces. In addition to galactic mergers, the expansion of the universe plays a crucial role in how we perceive its limits. The universe has been expanding since the Big Bang, and this expansion is accelerating due to a mysterious force known as dark energy. As galaxies move farther apart, our observable universe is continuously stretching, which means that the regions of space we can see today will be completely altered in the distant future. Areas of the cosmos that are visible to us now may eventually drift beyond our observational reach, leading us to redefine what we consider the edge of the universe. Moreover, the behavior of massive objects like black holes influences our perception on an even grander scale. Supermassive black holes found at the centers of galaxies can significantly affect the motion of stars in their vicinity, drawing them in and altering the gravitational landscape. Over time, the dynamics of these cosmic giants could lead to new formations of stars and even affect the flow of matter between galaxies, blurring the traditional boundaries we once imposed. Finally, as technology evolves and our observational capabilities improve, it allows us to explore deeper into space. Projects like the James Webb Space Telescope are opening new windows into the distant universe. Each discovery prompts us to redefine the outskirts of cosmic exploration. As we gather more data, our perspective will shift further, inviting us to consider not just the edges of the universe, but also the possibilities that lie beyond. In this ever-expanding universe, boundaries are merely a mirror of our current knowledge, a canvas for the next great cosmic inquiry. Dark energy is one of the most enigmatic concepts in modern cosmology. In simplest terms, it is the mysterious force that is believed to be responsible for the accelerated expansion of the universe. Observations show that not only is the universe expanding, but this expansion is occurring at an increasing rate. This surprising discovery was first made in the late 1990s, and it fundamentally changed our understanding of the cosmos. To visualize dark energy, think of it as an invisible energy that fills all of space and exerts a form of pressure. While normal matter and energy, which includes stars, galaxies, and gas, tend to clump together due to gravity, dark energy acts against this influence. It works to pull objects apart rather than allowing them to coalesce. This curious behavior suggests that dark energy constitutes around 70% of the total energy density of the universe, making it a dominant component in the cosmic puzzle. Despite its prevalence, dark energy remains poorly understood. Scientists have proposed various theories to explain its nature, including the possibility that it represents a constant energy density, or perhaps something more complex, like a dynamic field that changes over time. One of the leading ideas is based on the cosmological constant, a concept introduced by Albert Einstein. This idea posits that a constant energy density uniformly exists throughout space, causing the universe to expand at an accelerated pace. The implications of dark energy extend beyond mere expansion. If its influence continues unchanged, it poses fascinating questions about the eventual fate of the universe. Will galaxies drift apart indefinitely, leading to a cold and isolated cosmos? Or might dark energy evolve in the future, altering the dynamics of the universe entirely? As astronomers continue to chase answers, the quest for understanding dark energy remains one of the most tantalizing frontiers in science. Dark energy is a mysterious force that makes up about 70% of the universe and is driving its accelerated expansion. To put it simply, while gravity pulls objects together, dark energy seems to push them apart, making it a crucial component in our understanding of the cosmos. As researchers delve deeper into its properties, they realize that comprehending dark energy could unveil the fate of the universe itself. The implications of dark energy extend to significant cosmic events. For instance, its influence raises questions about the ultimate destiny of galaxies, stars, and even the fate of life as we know it. Will the universe continue to expand forever into a cold, desolate void? Or could it eventually collapse back in on itself in a scenario known as the Big Crunch? These possibilities are intertwined with the behavior of dark energy, highlighting its vital role in cosmic evolution. Moreover, understanding dark energy can also shed light on other cosmic phenomena, such as the formation and distribution of large-scale structures in the universe. As galaxies group together under the influence of gravity, dark energy counters that gravitational pull, creating a delicate balance. Understanding how this force operates can help us predict the future arrangement of galactic clusters and the cosmic web we see today. Dark energy serves as a key to unlock many of the universe's mysteries. As scientists measure its effects and attempt to unpack its essence, they are piecing together a narrative of cosmic history and future possibilities. Grasping this enigmatic force not only captivates our imagination, but is essential for understanding the very nature of the universe itself. Scientists use a variety of techniques to measure the effects of dark energy on the structure of the universe. One of the primary ways they do this is through the observation of supernovae, particularly a type known as type Ia supernovae. These stellar explosions serve as standard candles in the cosmos. Since they have a consistent intrinsic brightness, scientists can compare their observed brightness to how far away they are. This comparison allows for the measurement of cosmic distances and reveals how the expansion of the universe is accelerating due to dark energy. Another significant method involves mapping galaxies and their clusters across vast regions of space. Scientists utilize both ground-based and space-based telescopes to survey the distribution and movement of galaxies. By analyzing these structures and their gravitational interactions, researchers can understand how dark energy influences the overall expansion dynamics. This technique helps paint a picture of the cosmic fabric and the way it has evolved since the Big Bang. Gravitational lensing, another powerful tool, provides insights into the presence of dark energy. In this phenomenon, light from distant galaxies is distorted and magnified as it passes near massive objects, like galaxy clusters. By studying these distortions, scientists can infer the mass distribution of the foreground objects, which in turn reveals information about the geometry of space and the effects of dark energy. Lastly, cosmic microwave background radiation, the afterglow of the Big Bang, plays a crucial role in cosmological studies. By analyzing variations in this radiation, scientists can extract information about the universe's expansion history. Together, these methods form a multifaceted approach, helping researchers gain a deeper understanding of dark energy and its profound impact on cosmic structures. The idea of an ever-expanding universe stirs deep philosophical reflections and questions about our place in the cosmos. As we learn that the universe has been stretching since the Big Bang, it prompts us to ponder the limits of our understanding. If the universe continues to grow without end, what does that mean for our concepts of space, time, and existence? This ongoing expansion challenges traditional views of a stable, unchanging cosmos, suggesting instead that everything is dynamic and interconnected. In considering the vastness of an infinite universe, we encounter feelings of both awe and insignificance. It forces us to confront the question of humanity's relevance in such a boundless expanse. Are we mere specks on a cosmic scale? Or is our consciousness, our ability to ponder such concepts, what grants meaning to the universe? This juxtaposition can lead to existential reflections about purpose and connection in a seemingly indifferent universe. Moreover, the expansive universe brings about discussions on the nature of knowledge itself. If the universe is constantly evolving, can we ever reach a complete understanding of it? This challenges the philosophical idea of absolute truth. Scientists and philosophers alike grapple with the notion that our current theories and models may only be temporary snapshots of a reality that is always in flux. This idea raises probing questions about scientific inquiry and the limits of human knowledge. Finally, the concept of an ever-expanding universe invites us to think about the future of life and intelligence. What will become of civilizations as galaxies drift further apart? Will future beings gazing into the night sky even recognize a universe that looks drastically different from ours? These forward-looking inquiries frame a dialogue about the long-term implications of cosmic changes, nurturing a sense of curiosity that extends beyond our immediate existence. In this way, the expanding universe serves not only as a scientific phenomenon, but also as a catalyst for profound philosophical exploration. Dark energy is one of the most mysterious components of our universe, and scientists believe it makes up about 70% of the total energy content. It acts like a force that drives the acceleration of the universe's expansion. This phenomenon was first discovered in the late 20th century and has led to profound questions about the cosmos and its ultimate fate. By understanding dark energy, we might unlock key insights into the future of everything we know. The presence of dark energy suggests that the universe is not just expanding, but that its expansion is speeding up over time. This raises tantalizing possibilities for the universe's destiny. Many scientists propose scenarios based on the behavior of dark energy, as its properties could dictate whether the universe will continue to expand forever, slow down, or perhaps even reverse into a big crunch. The current evidence points toward an eternal expansion, leading to what's often termed the Big Freeze, where galaxies drift further apart until stars burn out, leaving a dark, cold cosmos. Another intriguing implication of dark energy is its potential variation over time or space. If dark energy's properties were to change, this could significantly impact the universe's expansion. Some models suggest that it might weaken over time, altering the trajectory of expansion. Conversely, if dark energy could become stronger, it might lead to dramatic scenarios such as a Big Rip, where the fabric of space-time tears apart entirely. Exploring these possibilities pushes the boundaries of our understanding and raises even more questions about the fundamental laws governing the universe. Ultimately, dark energy challenges us to rethink our cosmological models and the very fabric of reality. As we delve deeper into this enigmatic force, we not only gain insight into the universe's future, but also reflect on our place within it. Each discovery related to dark energy adds a new chapter to our ongoing cosmic story, inviting us to marvel at the universe's intricate and ever-evolving tapestry. Quasars, short for quasi-stellar objects, are remarkable astronomical phenomena that represent some of the most luminous and distant objects in the universe. Essentially, quasars are powered by supermassive black holes located at the centers of galaxies. As matter spirals into these black holes, it heats up and emits an incredible amount of energy, making quasars shine far brighter than their host galaxies. Some of these cosmic beacons can outshine entire galaxies, appearing as point-like sources of light similar to stars, which is how they got their name. The significance of quasars in cosmic history cannot be overstated. They serve as markers that help astronomers trace the evolution of the universe. Because many quasars are extremely far away, observing them allows scientists to look back in time. When we see light from these distant objects, we are often witnessing events that occurred billions of years ago, illuminating a period in the universe's history when stars and galaxies were forming and evolving rapidly. Quasars also provide insight into the conditions of the early universe. The light from these ancient quasars carries information about the cosmic environment at the time they were active. By analyzing this light, astronomers can learn about the distribution of matter, the nature of dark energy, and the processes that led to the formation of structures in the universe. They act like cosmic time capsules, locked in the light that has traveled across the universe for eons. Furthermore, the study of quasars contributes to our understanding of the cosmic web, the large-scale structure of the universe. They highlight the interactions between galaxies and the black holes at their centers. As researchers continue to unravel the mysteries surrounding these fascinating objects, they remain an essential focus in the quest to comprehend our universe's past and the forces that have shaped it over billions of years. Quasars, or quasi-stellar objects, are among the brightest and most distant objects in the universe. They are powered by supermassive black holes at the centers of galaxies that actively consume surrounding material. As this material spirals in, it heats up to enormous temperatures, releasing tremendous amounts of energy, often outshining entire galaxies. This remarkable luminosity makes quasars visible across vast distances, allowing astronomers to study them even if they are billions of light-years away from Earth. By observing quasars, astronomers can gain vital insights into the early universe. The light we receive from these distant beacons has traveled for billions of years, allowing scientists to peer back in time, closer to the universe's beginnings. This light carries information about the conditions and structures that existed when the quasars emitted it, offering clues about galaxy formation and the evolution of cosmic structures during a period known as the Cosmic Dawn. Furthermore, quasars provide a unique opportunity to study the intergalactic medium, the vast space between galaxies. As the light from a quasar passes through the gas and dust in this region, specific wavelengths get absorbed or altered. By analyzing these changes, astronomers can map the composition, density, and distribution of this elusive medium. This helps them understand how matter was distributed during the infancy of the universe and how galaxies formed and evolved in the context of cosmic history. By studying quasars, astronomers unlock a window into the early universe, exploring the conditions of its formation and the evolution of cosmic structures. This research not only enhances our understanding of a pivotal time in our universe's history, but also deepens our knowledge of fundamental astrophysical processes that continue to shape the cosmos today. Quasars are like ancient messengers, carrying with them the secrets of the universe's youth, helping us grasp the complexity and wonder of the universe itself. Quasars, short for quasi-stellar objects, are some of the most luminous and energetic phenomena in the universe. They are powered by supermassive black holes at the centers of distant galaxies, drawing in vast amounts of gas and dust. The lifespan of a quasar is generally estimated to be around 1 billion to several billion years. This duration may seem long, but in the grand timeline of the universe, it is relatively brief, especially when compared to the more than 13 billion years since the Big Bang. Understanding the lifespan of quasars offers profound insights into cosmic evolution. These incredible objects often signal a critical phase in a galaxy's life cycle, specifically when black holes are actively feeding. As the black hole consumes surrounding material, it radiates immense energy, outshining entire galaxies. This means that quasars can serve as markers for the formation and development of galaxies, allowing astronomers to trace their histories through the cosmos. As quasars begin to fade, they evolve into less active galactic nuclei, which can provide clues about how galaxies grow and change over time. The brightness of a quasar can also help scientists gauge the distance of its host galaxy, effectively allowing for a deeper understanding of how galaxies formed and evolved across billions of years. In this way, studying quasars allows astronomers to piece together the story of the universe, providing a glimpse into its past that enhances our overall picture of cosmic history. Moreover, the study of quasars sheds light on the environment surrounding black holes. The periods of activity and dormancy can illustrate how galaxies interact with their surroundings, influence star formation, and evolve over time. Thus, quasars are not just fascinating objects in their own right. They also act as beacons illuminating the intricate dance of cosmic evolution. Quasars are some of the most luminous and energetic objects in the universe, often found at the center of distant galaxies. They are powered by supermassive black holes, which can emit more energy than entire galaxies when they consume surrounding material. Because quasars are visible across vast distances, they serve as valuable beacons, allowing us to study the early universe and the processes that led to galaxy formation. Future observations of quasars can provide insight into the conditions of the early cosmos, particularly how galaxies and their central black holes evolved. By analyzing the light from these quasars, astronomers can glean information about the gas and dust surrounding them, which plays a critical role in the formation of galaxies. This data can reveal how quickly these objects grew and how that growth correlates with the development of their host galaxies. Additionally, observing numerous quasars across different points in time enables researchers to piece together a timeline of cosmic evolution. By identifying quasars at various distances, scientists can look back billions of years to understand how galaxies merged and formed under the influence of gravity and stellar processes. This historical perspective helps fill in the gaps regarding when and how different structures in the universe came into being. Through advanced telescopes and observational techniques, future studies of quasars will enhance our understanding of the intricate relationship between galactic development and black hole growth. The knowledge gained from these observations could revolutionize our comprehension of not just individual galaxies, but also the evolution of the universe as a whole. Each discovery leads us to a more profound appreciation of the cosmos and our place within it. Quasars, or quasi-stellar objects, offer a fascinating window into the vastness of the universe. These incredibly bright and distant astronomical entities are powered by supermassive black holes at the centers of galaxies. As material spirals into these black holes, it heats up and emits tremendous amounts of energy, sometimes outshining entire galaxies. The light from quasars can travel billions of light years to reach us, illustrating not just the distance but also the immense age of the universe. Studying quasars helps us map the cosmos in ways we had not thought possible. Given their brightness, they can often be seen from great distances, allowing astronomers to observe the formation and evolution of galaxies over time. By measuring the redshift of their light, scientists can determine how fast they are moving away from us, providing insights into the expanding universe. This vast scale of observation challenges our understanding of the universe's size and time, as we realize that we are seeing light emitted when the universe was still young. Moreover, quasars act as beacons, allowing us to probe the intergalactic medium, a region filled with gas and dark matter. As light from quasars passes through this medium, it interacts with the atoms and particles present, influencing the light's properties and revealing composition and density. This provides critical information about the universe's structure and the distribution of matter, further enhancing our comprehension of cosmic architecture. In contemplating quasars, we are reminded of our place in this grand scheme. The distances involved are so vast that they stretch the imagination. They encourage us to recognize that the universe is continuously evolving, with quasars serving as markers in the cosmic timeline. Every quasar we study enhances our appreciation of the scale of the universe, inviting us into the depths of space and time that go beyond our daily experiences. The shape of the universe has long intrigued scientists and cosmologists alike. Current theories suggest that the universe might have one of three primary shapes based on its overall geometry: flat, open, or closed. These shapes are fundamentally tied to the universe's density and the forces that act within it. Understanding these shapes gives us crucial insight into the universe's fate and its overall structure. A flat universe means it follows the laws of Euclidean geometry. This suggests that parallel lines will never meet, and that the angles of a triangle will always sum to 180 degrees. Data from the cosmic microwave background radiation, which carries the signature of the early universe, indicates that the universe is remarkably close to flat. This supports a model where the universe expands forever at a decelerating rate. An open universe, on the other hand, resembles a saddle shape. In this model, parallel lines diverge, and triangles can have angles that sum to less than 180 degrees. Open universes have a lower density, leading to an infinite expansion. This concept paints a picture of a universe that stretches endlessly as galaxies move apart over time. Lastly, a closed universe has a spherical shape. Here, parallel lines eventually converge, and the angles of a triangle can exceed 180 degrees. In this scenario, the universe would eventually stop expanding and start to contract. While current observations favor a flat model, ongoing research and exploration continue to refine our understanding, keeping the dialogue alive about the universe's infinite mysteries. The shape of the universe plays a crucial role in determining how cosmic events unfold, affecting everything from the trajectories of galaxies to the fate of the universe itself. Scientists often refer to three primary shapes: flat, closed, and open. Each of these geometrical configurations influences the overall behavior of gravity and expansion on cosmic scales, shaping the dynamics of all celestial bodies within the universe. In a flat universe, parallel lines remain parallel, and the total energy sums up perfectly to zero. This configuration, supported by observations of the cosmic microwave background radiation, allows galaxies to move away from each other at a consistent rate as the universe expands. Such a scenario means that cosmic events can be measured reliably, giving astronomers a way to forecast the movements of celestial objects over vast distances. A flat universe leads to a stable expansion that influences the lifespan of stars and galaxies, resulting in predictable evolutionary paths. On the other hand, a closed universe, which is finite and shaped like a sphere, exhibits different characteristics. Here, parallel lines eventually converge, and the pull of gravity can eventually stop the expansion of the universe, leading to eventual recollapse. This scenario could influence the future of cosmic events by heralding a big crunch, where all matter and energy collapse back into a singular point. In such a universe, stars might end their lives differently, and the conditions for black hole formation could vary significantly. An open universe, resembling a saddle shape, leads to an ever-accelerating expansion. It allows galaxies to drift further apart at an increasing rate, influenced by dark energy. This kind of structure impacts how cosmic elements interact, potentially leading to more frequent encounters between dark matter structures and galaxies. The expanding nature of an open universe ensures that distant cosmic events can happen far removed from the influences of nearby masses, creating a tapestry of cosmic interactions that continually evolve as time goes on. Understanding the shape of our universe not only deepens our knowledge of cosmic events, but also paints an intricate picture of our universe's fate. Scientists employ a variety of sophisticated methods to explore the vast and intricate structure of the universe. One of the primary techniques is through the observation of galaxies and their distributions across the cosmos. By mapping the locations and movements of billions of galaxies, astronomers can discern patterns in their arrangement. This helps scientists understand whether the universe is expanding uniformly or if it has regions of varying density, which can indicate the presence of dark matter and dark energy. Another crucial method is the use of telescopes designed to capture light from distant cosmic objects. These instruments, including both optical and radio telescopes, are essential for examining not just galaxies, but also clusters and superclusters. By studying the light emitted from these celestial bodies, scientists can analyze their composition, behavior, and historical context, allowing for a better understanding of the universe's evolution over time. This light also carries valuable information about the expansion rate of the universe, which is pivotal in cosmology. In addition to direct observation, scientists utilize advanced computer simulations to model cosmic structures. By inputting data gathered from observations, They can simulate how galaxies and other cosmic entities behave under the influence of gravity and other forces. These simulations help researchers predict how the universe will evolve in the future and test theories about its origins and fate. This synergy between observational data and computational power is crucial for unraveling the complex tapestry of the cosmos. Finally, physicists and cosmologists study the cosmic microwave background radiation, which is a remnant of the Big Bang. This faint glow permeating the universe carries information about the very early stages of cosmic development. By analyzing its fluctuations, scientists can glean insights into the universe's overall shape and the distribution of matter within it. This multifaceted approach, blending observation, simulation, and theoretical analysis, allows scientists to construct a clearer picture of the universe's large-scale structure and its mesmerizing intricacies. The shape of the universe is a fundamental question in cosmology, as it helps scientists understand not just the structure of the cosmos, but also its ultimate fate. When we refer to shape, we aren't talking about a simple geometric form, but a more complex understanding of how the universe is organized on a grand scale. Cosmologists consider three primary possibilities: a flat universe, a closed universe, and an open universe. Each of these shapes leads to different implications about the universe's expansion, its density, and the way galaxies interact with one another. One of the main reasons these open questions are significant is that they relate directly to the nature of space and time. A flat universe suggests that space extends infinitely without curves, while a closed universe implies a spherical shape that eventually wraps back on itself. Alternatively, an open universe features a hyperbolic shape that leads to continual expansion. Depending on the universe's shape, our models of gravity and the dynamics of cosmic evolution can change dramatically, influencing theories about the Big Bang, dark energy, and even the potential for a future collapse or endless expansion. Additionally, understanding the shape of the universe is essential for interpreting observational data. For instance, measurements from cosmic microwave background radiation, the afterglow of the Big Bang, offer insights into the universe's overall curvature. This information can help us estimate the total amount of matter and energy present in the universe and how it influences the cosmic fabric. Resolving these questions can lead to breakthroughs that deepen our comprehension of the fundamental laws of physics. Finally, the questions surrounding the universe's shape are interconnected with broader philosophical implications. As we ponder the universe's origin and ultimate destiny, we are not just exploring physical dimensions, but also delving into what it means to exist within this vast cosmos. The ongoing investigations in cosmology challenge our perception of reality, inviting us to reflect on our place in an ever-expanding universe. This intertwining of scientific inquiry and deeper existential questions keeps the field dynamic and relevant, echoing humanity's timeless quest for understanding amidst the stars. Advancements in technology play a pivotal role in enhancing our understanding of the universe's structure. Over the last few decades, we have witnessed an incredible evolution in observational tools, enabling astronomers and scientists to explore the cosmos with unprecedented clarity. Telescopes, once limited by the capabilities of human sight, have transformed into powerful instruments that can detect light from distant stars and galaxies billions of light-years away. Instruments like the Hubble Space Telescope have provided breathtaking images and data that reveal the complexity of cosmic structures such as nebulae, star clusters, and galaxies. By observing in wavelengths beyond human vision, like ultraviolet and infrared, these telescopes uncover details that are otherwise hidden due to Earth's atmosphere. This kind of observation is crucial for piecing together the universe's vast tapestry, helping to clarify how galaxies form, evolve, and interact over time. Additionally, advancements in computational power have transformed our ability to analyze the massive amounts of data collected by these telescopes. The universe is extraordinarily vast and complex, producing a complexity of phenomena ranging from black holes to cosmic microwave background radiation. With sophisticated algorithms and machine learning, scientists can process and interpret data more efficiently than ever before. This innovative approach yields new insights, leading to hypotheses that can be tested and refined, ultimately helping to unravel some of the universe's most profound mysteries. Moreover, Developments in technologies like gravitational wave detection are opening new avenues of research. Gravitational waves, ripples in spacetime caused by massive cosmic events, allow scientists to observe the universe in a completely different way. This technology not only gives us a glimpse of events like colliding black holes, but also enriches our understanding of the fundamental forces shaping the universe. Each advancement, whether in imaging, analysis, or detection, pushes the boundaries of our knowledge, weaving a more detailed and intricate picture of the cosmos we call home. Cosmic inflation is a fascinating concept in cosmology that describes a rapid expansion of the universe that occurred just moments after the Big Bang. Picture this. In the very early moments of our universe, it is believed that space itself underwent an exponential growth, expanding from a minuscule size to a vast expanse in a fraction of a second. This theory helps to explain how our universe transformed from a hot, dense state into the cold and structured cosmos we see today. One of the most intriguing aspects of cosmic inflation is how it addresses the uniformity of the universe. In our observable cosmos, we find regions of space that are remarkably similar in temperature and density, despite being separated by vast distances. This uniformity poses a challenge because light travels only so fast, and there hasn't been enough time since the Big Bang for all these distant regions to interact or influence one another. Cosmic inflation offers a solution, suggesting that these regions were once very close together before inflation stretched them apart dramatically. Inflation also helps to explain the flatness problem, which considers why the geometry of our universe appears so flat. A flat universe suggests that its shape is just at the critical density. Before inflation, any slight curvature in the universe would have been significantly amplified over time. However, the rapid expansion during inflation would have smoothed out any irregularities, leading to a balanced, flat universe on a grand scale. Cosmic inflation provides a powerful framework for understanding why our universe appears uniform and consistent. This theory not only fills in the gaps of our understanding regarding the early moments of the universe, but also unifies various observations in astrophysics, painting a complex picture that continues to captivate our minds and deepen our appreciation of the cosmos. Cosmic inflation is a theory that suggests our universe underwent a rapid expansion just after the Big Bang, blowing up by many orders of magnitude in a fraction of a second. This idea helps explain several puzzling features of the universe we observe today. One of the strongest pieces of evidence supporting this theory lies in the uniformity of the cosmic microwave background radiation, or CMB. This faint glow, which fills the universe, showcases a remarkably consistent temperature across the sky, leading us to question how such uniformity could exist without a mechanism like inflation to smoothing it out. Another compelling aspect is the large-scale structure of the universe. Observations show that galaxies are not randomly distributed. Instead, they form a web-like pattern with clusters and voids. Inflation predicts that quantum fluctuations during this brief explosive expansion would get stretched across vast distances, eventually leading to the clumps of matter that grew into galaxies. This connection between the tiny quantum world and the grand scale of the cosmos makes a powerful case for inflation. Tools like the Planck satellite have provided incredibly detailed maps of these tiny fluctuations, revealing patterns that align closely with what inflation suggests about the universe's expansion. This concordance gives researchers greater confidence that inflation is not just a theory, but a significant event in cosmic history. Lastly, the idea of inflation resonates with the current understanding of fundamental physics, particularly within the realms of particle physics and quantum mechanics. By theorizing that inflation was driven by a hypothetical field called the inflaton, scientists can tie together concepts from both cosmology and particle physics. This synthesis not only enriches our comprehension of the universe's origin, but also encourages further exploration into the laws that govern the cosmos. The study of cosmic inflation offers fascinating possibilities for understanding the evolution of the universe. Cosmic inflation refers to a brief period in the universe's history, shortly after the Big Bang, when it expanded exponentially faster than the speed of light. This rapid expansion helps to explain several key observations about the universe, such as its large-scale uniformity and the distribution of galaxies. By analyzing this era, scientists can gain insights into how the universe became structured as we see it today. One of the most intriguing aspects of inflation is the way it might have set the initial conditions for the universe we inhabit. During inflation, tiny quantum fluctuations could have been stretched to cosmic scales. These fluctuations eventually seeded the large-scale structures of the universe, influencing how galaxies and clusters formed. By studying the specific patterns left behind, known as cosmic microwave background radiation, scientists can glean information about the inflationary period and its impact on the universe's expansion. Moreover, continued research into cosmic inflation could provide clues about the fundamental forces and particles that shaped the early universe. By probing the physics behind inflation, researchers hope to connect our understanding of cosmic events with theories of particle physics. This interplay not only expands our knowledge of the universe's beginnings, but may also lead to revelations about the nature of dark energy and dark matter, which remain two of the most enigmatic elements in contemporary cosmology. As scientists refine their observations and experiments, perhaps through advanced telescopes or space missions, the insights gained from studying cosmic inflation could very well reshape our understanding of the universe's evolution. With every discovery, we are unraveling more of the profound mysteries surrounding our existence, pushing the boundaries of what we know and inviting fresh questions about the cosmos. The journey of exploration continues, bringing the wonders of the universe closer to our grasp. Understanding the timeline of cosmic inflation is crucial for grasping not only the origins of our universe, but also its potential future. Cosmic inflation occurred just fractions of a second after the Big Bang, marking a period of rapid expansion that set the stage for everything we observe today. By studying this early universe phenomenon, scientists uncover how the universe evolved from a hot, dense state into the vast cosmos we know now. This knowledge creates a foundation for predicting future cosmic events. The effects of cosmic inflation extend beyond the initial growth of the universe. It provides insight into the uniformity observed in the cosmic microwave background radiation, the faint glow that stems from an early era of the universe. Understanding the variations in this radiation helps cosmologists learn about the distribution of galaxies and the large-scale structure of the universe. This connection between inflation and today's universe is essential for anticipating how it might behave in the future. Furthermore, cosmic inflation theories suggest that the universe may still be expanding. If this expansion continues indefinitely, it could lead to scenarios such as the Big Freeze, where galaxies drift apart and stars eventually burn out. Alternatively, if certain conditions shift, we may encounter different outcomes like a Big Crunch, where the universe collapses back on itself. By examining inflation, scientists build a framework to consider these possibilities and the conditions that could lead to each scenario. Cosmic inflation is not merely a historical chapter. It acts as a lens through which we can view the universe's past, present, and future. As we delve deeper into understanding this chapter, we lay the groundwork to answer profound questions about the ultimate fate of everything we know and explore the cosmos yet to be discovered. Cosmic inflation, the theory suggesting a rapid expansion of the universe just after the Big Bang, has gone through significant evolution in how we perceive it, especially with recent discoveries. Initially proposed in the early 1980s, this concept aimed to solve several puzzles about the universe's structure and uniformity. It explained why distant regions of the cosmos appear so similar, despite being too far apart to have interacted since the universe began. As our observational tools improved, so did our understanding of the early universe. Observations from telescopes like the Hubble Space Telescope and various satellite missions, such as the Planck satellite, provided detailed measurements of the cosmic microwave background radiation. This radiation, a remnant from the early universe, carries fingerprints that support the inflationary theory. The precise data gathered has allowed scientists to refine their models, providing clearer parameters about the inflationary period's duration and intensity. Interestingly, recent discoveries have introduced new complexities. For instance, some findings have suggested that inflation might not be a singular event, but rather a continuous process involving various models, such as eternal inflation. This idea posits that while our observable universe underwent inflation, other regions could be inflating simultaneously, leading to a multiverse scenario. This expands our understanding of what the cosmos could be, presenting an intriguing possibility where many universes exist, each with its distinct properties. Ultimately, our perception of cosmic inflation is becoming increasingly sophisticated. We are moving from viewing it as a somewhat abstract explanation to a more nuanced, dynamic interplay of processes shaping our universe. With ongoing research and exploration, our understanding continues to deepen, inviting us to ponder the very nature of reality and our place within this vast cosmic tapestry. The discovery of future exoplanets promises to be a transformative force in our understanding of cosmic events. As we continue to identify and study these distant worlds, we gain valuable clues about the formation and evolution of planetary systems, including our own. Each new exoplanet can teach us something unique about the conditions in which planets form, the materials they are made from, and how they interact with their star systems. Moreover, some exoplanets exist in what's known as the habitable zone, where conditions might support liquid water and potentially life. This invites a closer examination of the variety of environments that can exist beyond our solar system. By understanding the atmospheres, compositions, and climate conditions of these exoplanets, we can make educated inferences about the historical events that shaped them, including possible catastrophic cosmic events like asteroid strikes, stellar flares, or the influence of nearby supernova. The implications of these findings extend beyond planetary science. For instance, studying exoplanets can enhance our comprehension of the processes that drive cosmic events on a larger scale, such as star formation and galactic evolution. By placing these worlds in the broader context of their galaxies, we can piece together how cosmic forces influence not only stars and planets, but also the very structure of the universe itself. As telescopes become more advanced and our technique for studying distant worlds improves, the future of exoplanet discovery will likely redefine our place in the universe. Each new planet found is not just an isolated relic, but a key that might unlock the mysteries of cosmic history, illuminating not only how these planets evolve, but also what they reveal about the universe's journey through time. The study of exoplanets, or planets that exist outside our solar system, plays a crucial role in shaping our understanding of habitability beyond Earth. Astronomers have discovered thousands of these alien worlds, some residing in what is known as the Goldilocks zone, an area around a star where conditions might be just right for liquid water to exist. This is a fundamental requirement for life as we know it, making these exoplanets prime candidates in the search for habitable environments. As we learn more about the atmospheres and compositions of these distant planets, scientists are able to speculate about the potential for life. By analyzing the light that filters through an exoplanet's atmosphere when it transits in front of its host star, researchers can glean insights into its chemical makeup. This meticulous study gives us clues about not only the planet's surface conditions, but also the possibility of biological processes at play. Moreover, these discoveries challenge and refine our existing theories about habitability. For many years, people primarily thought life could only thrive under conditions comparable to those on Earth. However, the diversity of exoplanets reveals that habitability might not adhere strictly to these Earth-like standards. For instance, some planets orbiting red dwarf stars could experience extreme conditions or high radiation levels, yet may still harbor life in ways we haven't yet considered. This expanding knowledge encourages us to think beyond our own planet when contemplating the universe's potential for life. The prospect that habitable conditions might arise under a variety of circumstances invites both scientists and enthusiasts to imagine the possibilities. In doing so, the study of exoplanets not only enhances our understanding of what makes a planet livable, but also pushes the boundaries of our imagination in terms of what life might look like elsewhere in the cosmos. The search for distant exoplanets, those intriguing worlds beyond our solar system, has been truly revolutionized by a wave of technological innovations. One of the most monumental advancements is the development of space-based telescopes, such as the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, often known as TESS. These telescopes employ a method called photometry, which involves measuring the brightness of stars over time. When a planet crosses in front of its host star, it blocks a tiny fraction of the light, causing a measurable dip. This has allowed astronomers to discover thousands of exoplanets, enhancing our understanding of their diversity and composition. Another key innovation is the use of spectrometry to analyze the atmospheres of these distant planets. By observing the light that passes through or reflects off a planet's atmosphere, scientists can determine its composition. This technique can reveal the presence of various gases, like oxygen or methane, which might indicate the potential for life. The James Webb Space Telescope, launched recently, is expected to enhance these capabilities even further, providing detailed insights into the atmospheres of smaller Earth-like exoplanets. Advancements in ground-based telescopes also play a significant role in exoplanet research. These instruments have become incredibly sophisticated, equipped with adaptive optics that cancel out the blurring effects of Earth's atmosphere. This allows astronomers to observe and gather data from fainter stars and smaller planets than ever before. Projects like the Extremely Large Telescope, set to begin operations in the coming years, aim to push the boundaries of our ability to detect and analyze exoplanets. Artificial intelligence is another exciting frontier aiding this exploration. With vast amounts of data collected from various missions, machine learning algorithms are now assisting scientists in sifting through and identifying potential exoplanets. These algorithms can spot patterns and anomalies in the data that might suggest the existence of distant worlds, streamlining the discovery process. As technology continues to evolve, our understanding of the universe and the potential for finding new worlds will only expand, opening doors to answers about the cosmos and our place within it. Understanding exoplanets, planets that orbit stars outside our solar system, has become a fascinating frontier in astronomy. Documenting their specific characteristics is crucial for several compelling reasons. First and foremost, detailed information about these distant worlds enhances our knowledge of their potential to support life. Features such as size, composition, atmosphere, and distance from their parent star help scientists assess whether these planets fall within the so-called habitable zone, where conditions might be right for life as we know it. Moreover, gathering data on exoplanets allows researchers to compare them with planets in our own solar system. By looking at their atmospheres, for instance, scientists can better understand the processes that govern planetary formation and evolution. This comparative analysis can reveal why some planets become rocky and earthly, while others turn into gas giants. Such insights help us piece together the puzzle of how different types of planets emerge and what factors influence their development. Another vital aspect of documenting exoplanet characteristics involves studying their atmospheres and climates. By identifying the chemical compositions of these atmospheres, researchers can search for key indicators of life, like oxygen or methane. Understanding atmospheric dynamics also aids in forecasting weather patterns on these planets, which is essential for predicting their long-term habitability. Furthermore, these investigations can lead to the discovery of potentially Earth-like planets, where complex chemistry could unfold. Finally, detailed documentation creates a rich database that can facilitate future explorations and technological advancements. As we develop more sophisticated telescopes and observational techniques, having a solid foundation of data allows scientists to refine their hypotheses and focus on more promising targets in the vast expanse of space. This ongoing cycle of discovery and documentation fuels the drive to understand not just our own solar system, but the universe as a whole, making the study of exoplanets a thrilling and vital aspect of modern science. The study of exoplanets, those fascinating worlds beyond our solar system, has already transformed our understanding of the universe. As we look ahead to the next few decades, we can anticipate remarkable advancements in this field, fueled by cutting-edge technology and an ever-growing scientific community. The next generations of telescopes, like the James Webb Space Telescope, are only the beginning. These instruments are designed to observe the atmospheres of exoplanets in unprecedented detail, allowing us to determine their chemical compositions and even identify potential signs of life. In addition to advancements in technology, the methods of discovering and studying exoplanets will evolve significantly. Current techniques, such as the transit method and radial velocity measurements, will be complemented by new approaches, including direct imaging. This will enable scientists to capture actual photographs of exoplanets and analyze their surfaces and atmospheres, revealing more about their climates and geology. The hunt for Earth-like planets in habitable zones is likely to become even more refined, with an emphasis on finding worlds that mirror our own in terms of conditions suitable for life. Collaboration across nations and disciplines will play a crucial role in these advancements. Universities, research institutions, and space agencies will increasingly work together, creating a global network dedicated to exoplanet discovery. Citizen scientists may also join the effort, contributing to the analysis of vast amounts of data generated by space missions. Engaging the public has the potential to inspire the next generation of astronomers, encouraging diverse viewpoints and innovative ideas that will enhance our understanding of planetary systems. As we progress, ethical considerations will come into play. The prospect of potentially habitable exoplanets raises questions about our responsibilities should we find signs of alien life. Conversations about planetary protection and identifying signals from extraterrestrial civilizations will gain prominence, reflecting our growing awareness of our place in the cosmos. The future of exoplanet research promises not only to broaden our knowledge, but also to deepen our understanding of life in the universe and our role as stewards of our own planet. The high-energy particles originating from outer space, and they mostly consist of protons, with some being heavier atomic nuclei, electrons, and even gamma rays. These particles constantly bombard Earth, colliding with the atmosphere at nearly the speed of light. This interaction produces a cascade of secondary particles which can be detected at ground level. The very first cosmic rays were discovered in the 1910s, and their study has since revolutionized our understanding of the universe. One fascinating aspect of cosmic rays is their energy. Some are incredibly powerful, with energies millions of times greater than those produced in human-made particle accelerators. These high-energy particles are believed to originate from various sources in the universe, including supernova explosions, active galactic nuclei, and even more mysterious phenomena like gamma-ray bursts. By studying cosmic rays, scientists can glean valuable insights into these energetic processes and the nature of the cosmos itself. Cosmic rays are also significant for astrophysical research because they serve as messengers from the farthest reaches of the universe. They carry information about their sources and the conditions in space. When scientists analyze the composition and behavior of these particles, they can infer details about cosmic magnetic fields, the structure of the universe, and even the fundamental properties of particles themselves. For instance, certain cosmic rays can help researchers understand the conditions prevalent in supernova remnants, shedding light on stellar evolution. Furthermore, cosmic rays play an essential role in understanding the fundamental forces of nature. They are involved in processes like the formation of clouds and potentially contribute to climate patterns on Earth. As researchers continue to investigate these enigmatic particles, we move closer to unlocking the mysteries of the cosmos, revealing the complex dance of matter and energy that shapes our universe. Cosmic rays are indeed the universe's way of communicating with us, and every particle tells a story waiting to be uncovered. Cosmic rays are high-energy particles that travel through space and, upon entering our atmosphere, interact with matter in fascinating ways. These energetic particles, primarily protons but also helium nuclei and heavier atomic nuclei, originate from various cosmic sources, including supernovae, active galactic nuclei, and even our Sun during solar flares. When they collide with molecules in Earth's atmosphere, they can create a cascade of secondary particles, resulting in a shower of radiation that sweeps across the sky. As cosmic rays strike the atmosphere, they collide with atoms, producing new particles such as muons and pions. This interaction generates an impressive number of secondary particles that can reach the surface of the Earth. Remarkably, muons, which are heavier relatives of electrons, are able to penetrate through the atmosphere and even travel several kilometers into the ground before they ultimately decay. It is estimated that every square meter of the Earth's surface is bombarded by thousands of cosmic ray particles each day. When cosmic rays interact with materials on the ground, including biological tissues, they can cause ionization. This means that they can strip away electrons from atoms, potentially damaging or altering molecular structures. This process is especially important in fields like medicine and genetic research. For instance, some studies have suggested that cosmic rays might have a role in mutations in DNA. However, Earth's atmosphere and magnetic field act as protective barriers, reducing the intensity of cosmic rays and allowing only a fraction to reach the surface. Ultimately, cosmic rays play a crucial role in the universe and provide insights into the intricate workings of matter, energy, and even the origins of our universe. By studying these particles, scientists not only learn about cosmic phenomena, but also enhance our understanding of fundamental physics and the potential impact on both biological systems and technological infrastructure on Earth. So the next time you look up at the sky, consider that high-energy particles are constantly raining down, revealing secrets of the cosmos. Cosmic rays have captivated scientists for decades, not just for their mysterious nature, but also for the vast knowledge they can impart about our universe. Recent discoveries suggest that these high-energy particles originate from unusual sources that could reshape our understanding of their origins. Traditionally believed to emerge from supernovae or other galactic phenomena, new research points towards more exotic origins that could include gamma-ray bursts or even interactions from active galactic nuclei. In a groundbreaking study published not long ago, researchers highlighted findings from the Ice Cube Neutrino Observatory in Antarctica. This facility detected neutrinos, which are elusive particles that can give us crucial clues about cosmic ray sources. These neutrinos appear to have originated from a specific region of the sky, suggesting that certain types of massive energetic events are contributing to the cosmic ray background we observe. This is a significant shift in our perception that may lead us to consider a broader array of celestial phenomena as potential origins. Furthermore, recent studies on the composition of cosmic rays have revealed surprising insights. By analyzing the isotopes of heavy elements within cosmic rays, scientists are gathering evidence that these particles might be accelerated in environments we previously thought were not energetic enough. For instance, the involvement of magnetic fields in galaxy clusters could be more crucial than once believed, effectively channeling the energy needed to accelerate these cosmic rays to such extraordinary speeds. Collectively, these discoveries do not just refine our understanding of cosmic rays, they open up new avenues for exploration in astrophysics. By challenging traditional models and emphasizing the complexity of cosmic events, we are reminded of the vast and intricate web that constitutes our universe. As we delve deeper into understanding cosmic rays, we may find ourselves unearthing revelations about the fundamental processes that govern the cosmos and our place within it. Cosmic rays are high-energy particles originating from beyond our solar system, primarily from supernovae, active galaxies, and even neutron stars. These particles constantly bombard Earth, but their intensity can vary. When there is a surge in cosmic ray activity, it often indicates some significant cosmic event taking place, or it may signal changes in the solar activity, hinting at upcoming phenomena worth monitoring. For instance, a substantial increase in cosmic rays can sometimes correlate with solar flares or coronal mass ejections from our Sun. These solar explosions release vast amounts of energy and charged particles into space, and when directed toward Earth, they can disrupt our planet's magnetic field and affect satellite operations, power grids, and even communications. So by monitoring cosmic rays, scientists can gain advance warning of these solar eruptions. Moreover, cosmic rays can provide essential clues about more distant cosmic events, such as the explosion of a supernova or the collision of neutron stars. When these violent events occur, they can produce a pulse of cosmic rays that reaches Earth. By studying these cosmic rays, researchers can learn about the properties of the objects involved, such as their composition and the energies involved in their cataclysmic destruction. Tracking cosmic rays adds a critical piece to the puzzle of monitoring our universe. The changes in their activity can serve as beacons alerting scientists to both imminent solar phenomena and the reverberations of spectacular cosmic events elsewhere in the universe, reminding us of the interconnectedness of all cosmic occurrences. As we look to the future, advancements in technology hold great promise for enhancing our ability to detect and study cosmic rays. Cosmic rays are high-energy particles that originate from outside our solar system, and they provide valuable insights into the workings of the universe. Improved detection techniques and instruments will allow us to capture more detailed data about these mysterious particles and their origins. One exciting development is the potential for larger, more sensitive detectors. Future cosmic ray observatories could be equipped with expansive arrays of sensors capable of identifying the faint signals produced when cosmic rays interact with our atmosphere. By increasing the area of detection, we can collect more data, leading to a better understanding of the energy spectrum and the distribution of these high-energy particles. Advanced materials, such as superconductors, may also enhance sensitivity and reduce noise in detection systems, allowing for clearer signals from cosmic rays. Moreover, innovations in artificial intelligence and machine learning could dramatically improve data analysis. With the vast amounts of information generated by cosmic ray detectors, AI could help sort through this data much more efficiently than traditional methods. Machine learning algorithms can identify patterns and anomalies that might be missed by human researchers, enabling us to uncover new insights about cosmic ray sources and their interactions with other cosmic phenomena. Finally, collaborations between different scientific institutions globally could lead to the development of a network of interconnected observatories. By pooling resources and data, scientists can create a more comprehensive picture of cosmic rays. This network approach would enhance our ability to track cosmic rays in real time and share findings across borders, leading to groundbreaking discoveries about the fundamental forces of our universe. The future of cosmic ray research is bright, driven by technological innovations that will deepen our understanding of the cosmos. The search for extraterrestrial intelligence, often abbreviated as SETI, ignites a profound curiosity about our place in the universe. This quest isn't just about finding aliens, it intertwines deeply with our understanding of cosmic events and the broader tapestry of life in the cosmos. As we study the universe, its galaxies, stars, and planets, we also glean insights into the conditions that might support life beyond Earth. Every cosmic event, from the birth of stars to the formation of planetary systems, provides vital clues about the potential for life. For instance, supernova explosions scatter elements across the universe, enriching the cosmic environment with the building blocks of life. Understanding these events helps scientists identify where life might emerge, making it possible to target specific locations in our galaxy that exhibit the right conditions. Moreover, cosmic events such as asteroid impacts or the violent eruptions of black holes can have dramatic effects on planetary atmospheres and environments. By studying these events, researchers can better understand the resilience and adaptability of life. If we know how life might survive extremes on our own planet, we can extend those ideas to other worlds, hypothesizing about what life could look like elsewhere. Ultimately, the search for intelligent life is not just a look outward, but a reflection on our history as a species. Each discovery about the universe informs our understanding of whether we are alone or whether the signals we seek might be out there, waiting for us to listen. Thus, the pursuit of extraterrestrial intelligence is inextricably linked to our cosmic narrative, urging us to explore and understand the universe as a richly interconnected ecosystem of existence. The quest to detect extraterrestrial life is not just a matter of having the right tools. It is also influenced by a variety of cosmic events and phenomena that can either enhance or hinder our efforts. On one hand, certain astronomical occurrences can improve our chances. For instance, the discovery of exoplanets in the so-called habitable zone of their stars is one significant boost. These zones allow for the presence of liquid water, a key ingredient for life as we know it. Furthermore, advancements in technology, such as powerful telescopes and space probes, have enabled us to glean more information from distant worlds, enhancing our understanding of their atmospheres and potential habitability. Conversely, there are cosmic events that pose significant challenges to our search. For example, gamma-ray bursts are incredibly intense explosions that can release more energy in a few seconds than the sun will emit in its entire lifetime. If such an explosion were to occur close to Earth, it could strip away our atmosphere and drastically affect life here, thus chilling our exploration efforts. Similarly, supernovae, the explosive deaths of massive stars, can produce shockwaves and radiation that could potentially damage the protective layers around planets, making them less hospitable for life. The activity of supernovae also introduces a fascinating complexity. When these events occur in our cosmic neighborhood, their radiation can create havoc in stellar nurseries, the very places where new stars and potentially habitable planets are born. A nearby supernova could trigger some of those nurseries to form stars quicker than they otherwise would, but not all of those new stars will end up hosting friendly planets. This creates a mixed bag of opportunities and dangers in our cosmic backyard. Lastly, solar activity and its associated phenomena, such as solar flares and coronal mass ejections, can also interfere with our observations. These events can disrupt the electromagnetic signals that we depend on to communicate with space probes or gather data from distant planets. Such disruptions could lead to lost signals or corrupted data, which would hinder our understanding of the cosmos. As we continue our search for extraterrestrial life, we must remain aware of these cosmic variables, knowing that they play a vital role in this grand quest. The question of whether we are alone in the universe has captivated humanity for centuries. Discovering intelligent life beyond our planet would fundamentally change our understanding of existence and our place within the cosmos. Such a finding could challenge our scientific, philosophical, and theological beliefs, compelling societies to reconsider what it means to be human and the very fabric of life itself. Moreover, the implications of finding intelligent life extend beyond mere curiosity. It touches on questions of communication and understanding. If we encounter an intelligent civilization, how we choose to communicate with them may redefine our approaches to language, culture, and even ethics. The methods and technologies we use could either foster peaceful exchanges or lead to misunderstandings. Consequently, preparing for these interactions is crucial, as our response could shape interstellar relations and humanity's reputation across the galaxy. There's also the potential impact on technology and innovation. By studying intelligent life forms, we might gain insights into advanced technologies that could enhance our own capabilities. Imagine the medical, environmental, or space travel technologies inspired by extraterrestrial civilizations. The quest for knowledge in relation to other intelligent beings could push humanity to explore new frontiers beyond our current understanding. Lastly, the quest for intelligent life encourages unity among humans. The vastness of the universe serves as a reminder of our shared humanity, prompting collaborative efforts in science and exploration. When we come together to explore the cosmos, we focus less on our differences and more on our collective aspirations. The exploration of intelligent life is not just about finding others, it's about enhancing our own human experience. The search for extraterrestrial intelligence is an awe-inspiring endeavor, yet it is fraught with challenges rooted in our understanding of time and distance. Space is vast, and the distances between stars and galaxies are not only immense, but also difficult for us to fathom. For instance, even at the speed of light, which is the fastest speed known to us, it takes more than 4 years to reach the nearest star to Earth, Proxima Centauri. This reality raises the question, how can we possibly communicate or travel to other civilizations that might be light years away? Time complicates matters further. The universe is approximately 13 billion years old, and light from distant galaxies takes billions of years to reach us. This means that when we observe these galaxies, we are looking into the distant past rather than the present. If there are civilizations out there, they may have existed or evolved millions of years ago, or they may be just beginning to emerge now. By the time we receive signals or messages, those civilizations may have changed, disappeared, or even evolved into something entirely different. This disconnect in time makes it challenging for us to make meaningful connections with potential neighbors in the cosmos. Moreover, the vast temporal and spatial scales mean that the searches we currently undertake through radio signals or laser transmissions are monumental undertakings. Scientists employ massive telescopes and arrays to listen for signals from space, hoping to hear from an intelligent civilization. However, these signals may take years to arrive, and if they are faint or infrequent, the chances of detection become increasingly slim. It's like trying to tune into a distant radio station while surrounded by noise. One must listen closely, often for a very long time, to catch a small glimmer of something significant. Our exploration for extraterrestrial intelligence is profoundly shaped by the realities of time and distance. As we peer out into the universe, we are not only searching for life, but also wrestling with the very nature of existence across the cosmic landscape. Each distant star and galaxy may hold the potential for stories and histories we cannot fully grasp, illustrating just how remarkable and complex our search truly is. As we gaze into the vastness of space, the quest to connect with potential extraterrestrial intelligence feels both daunting and thrilling. Future advancements in communication technology promise to transform this endeavor in remarkable ways. Imagine harnessing the power of quantum communication, which allows for instantaneous information transfer over vast distances. This kind of technology could significantly enhance our ability to send messages to distant stars, minimizing delays caused by the immense distances involved. Moreover, the refinement of radio telescope technology could provide us with sharper and more precise listening capabilities. Currently, we rely heavily on radio waves to search for signals from other civilizations. With better sensitivity and resolution, future telescopes may detect weaker signals that are currently imperceptible. This could open up entirely new avenues for exploration, revealing the chatter of alien civilizations that lie beyond our reach right now. Artificial intelligence also plays a crucial role in this transformation. As we develop smarter algorithms, they could analyze incoming data more efficiently than human researchers can. These advancements might help us sift through noise and identify genuine signals that indicate the presence of extraterrestrial life. This increased capability would make our search for intelligent life not just broader, but much deeper, allowing us to focus our efforts more strategically. Finally, as global cooperation in science and technology continues to grow, we can pool resources and knowledge from around the world, enhancing our collective ability to explore. Collaborative projects could lead to the development of more powerful telescopes and spacecraft that are equipped with cutting-edge communication tools. As the fabric of our communication technology strengthens and expands, so too does our capacity to reach out and potentially speak to the stars. The future looks promising, and who knows what conversations await us among the cosmos.